So welcome to this talk about phase or loudspeaker phase. It says that I'm doing it with Erin of Erin's Audio Corner. I'm not doing that for now because this will be a rather long video. Instead, we will be discussing at a later point in time some of the findings from this presentation. This is largely a lecture on signal processing. So I actually want to thank a couple of my former professors because they really got me interested in signal processing with a special focus on electronics and signal processing in electronics because that was what I was studying. I want to point out Klaus, who taught us about passive and active analog filters. A lot of the signal processing that I'm presenting here is really what Klaus taught us many years ago. And also Ole, who was on the more electronic side of signal processing. We looked very much at transfer functions and how to find them for different electrical circuits. So a big thanks to these two guys and in general to the professors I had when I studied. I wish there was one book that I could point to and say, if you want to know about loudspeaker phase, this is the book that you need to read. I had to look in many different books and work with loudspeakers and transducers in general for many years to sort of build the picture that I have in my head. If you want to start somewhere, I would probably say this blue book here by Stephen Smith. If you don't really have much signal processing knowledge, that's a good way to start, and I think you can download it for free actually. There are of course some more classic signal processing books. They are also good. I think in general signal processing books don't cover enough transient behavior. For that, I think you would be helped by looking at like electronics books and electric circuit theory. They typically have a better in-depth description of transient behavior. And we will be looking at transient behavior later on. It's a good thing to know about Fourier transform, Laplace transform, and these things. But let's see how far we can get with the presentation alone. About me, you can pause and look at what I have here. I have my own company where I do mathematical modeling of different products. So virtual prototyping, you could say. I'm a COMSOL certified consultant, and a lot of the graphs and plots you'll see here today I've made in the COMSOL environment. Also, I'm not a loudspeaker designer. I don't consider myself a loudspeaker engineer. I am more involved in some projects where a lot of development has been done, but there's some kind of problem, some dips or peaks or whatever in the frequency response, and someone needs to find a quick solution for that. And then some more complex work like shape and topology optimization, like I'm showing here, that you can greatly transform the output of, for example, a waveguide if you allow a new structure to be built that you put on top of that. So in that sense, I do work with loudspeakers, but it's not my primary focus in any way. So I won't be talking a lot about measurements and the issues with measuring loudspeakers. That's not really what I do. I'm more on the theoretical side of things and as I said, the mathematical modeling of things. Here's an overview of some of the videos that I have done with Erin or planned to do with Erin. You could say that this one on phase should actually have been the first one. Signal processing is the first step towards understanding loudspeakers, but now it's been presented in a different order. If you have suggestions for things you want to see, we can look at that. So if you don't really know about phase or magnitude, the motivation might not really be there to getting to know more about it. But the phase and magnitude are two aspects of what we call a transfer function. That the transfer function describes a system. And very often magnitude response is the one we look at, and then the phase is sort of thrown away and seen as not being too important. And so what I want to show here is that that's really a shame, because the phase is more interesting in some aspects. It holds all of the temporal information, the way that transients are going to look, for example. That's not entirely determined by the phase, but magnitude also comes into play, but it's, as I write here, heavily influenced by phase. And also phase changes alone can change the output amplitude, even though you have a constant gain at all frequencies. And we can illustrate that. So if you just look at magnitude first, so there's a kind of a classical example. If you have a square signal, note that I don't say square wave, and we'll get to that later. A square signal like the blue one here, that is really composed, or you can think of it as being composed of infinitely many harmonic sinusoids. So discrete frequencies, but infinitely many. Imagine that you cut away all magnitudes above a certain frequency, and all you're left with are these three sinusoids that are sort of the first three building blocks of this square signal. If you add them up, you get this blue signal here on the right. And you can see you have a little bit of an overshoot. It's worst for if you only have the first fundamental here. But removing frequency components can lead to a greater output amplitude-wise. You've lost energy, but you've gained some amplitude. And that's just because of how the signals that are left sum up. But also, if you manipulate the phase of these three signals, like they all get a phase shift, and we'll get to what a phase shift is. But changing the phase alone will also typically lead to a different amplitude output. You can see you have a much higher output now that you've changed the phase. And even if you have all of the components, all of the sinusoids that build up this sine, or this square signal, if you start meddling with the phase, you're going to get something that doesn't look like a square signal anymore. And you can basically get as much overshoot as you want to if you align all of these frequency components in the proper way. Not that you probably want to, but it will be heavily distorted even if the magnitude response is flat. So that's at least one motivation for looking at phase. The temporal stuff we'll get to. So I've divided it into, 5 different subtopics. So it's numbers first, then signal systems and fields, which is a bit unusual, but we'll see why. Then transfer functions, delay, and loudspeaker phase. I might have to jump a little in between the two, but I think it's been split out fairly nicely between those 5 different ones. So let's start out with numbers. I think a good way to think about numbers, because we'll get to some more complicated number theory later on. I think a good way to think about numbers is to think about them as abstractions. They're not really real. They're just a convenient way for us to do calculations, but not essentially a real thing. I think that's going to help later on when it becomes more complicated to think already now about real numbers as an abstraction that we have in our heads. There's a great bit of history about negative numbers and zero. And the very beginning of numbers, all numbers were thought of as being positive. No one could imagine anything else. But let's say our starting point is that we have positive numbers, negative numbers, and zero. And then we have some number somewhere. I just put it to 1.5. So we're moving along this line here, and that's basically what we are confined to. But we can also, if we have some more mathematics knowledge, we can also look at vectors, like these spatial vectors, where each vector has, in essence, two numbers in this 2D example. Two numbers assigned to each vector to describe how much did I go in one direction and how much did I go in a perpendicular direction, for example. So for each of these two vectors, we have two numbers, so 4 numbers in total. And also we know that if we align them, so one arrow first and then the other one put afterwards, we can get the sum of the two. And that sum is really the sum in one direction and the sum in another direction. So there is a way of thinking about addition in this sense of summing the one characteristics and then summing another characteristics. In this case, two different directions, you could say. And then you could say, well, our number line is just one line. We could think of a number here as a vector. It just points in a trivial direction. But we could think about this as a vector of length 1.5. So why am I saying that? Well, one thing to note is that we could now think of a negative number as a flipped version of a positive number, meaning something has been rotated 180 degrees in the vector sense that we have here. So why would we think about it like that? Well, that is sort of to open up our minds a little bit and say, well, what if it's not 180 degrees? What if there's something in between here? But you can see there isn't anything out here because we just have a number line. It's a 1D thing. But what if? And this is where polynomials come in, because maybe you have tried to solve polynomials back in school. And if you take like a second order polynomial like this one, there's this well-known formula for finding roots. So that's where for given A, B, and C, there are certain x's that will give you that the final output is 0. And sometimes we find two solutions to that, and there are just these instances where we don't. We have to say there's no solution. If we plot a function like that, we'll see that the roots are really where this curve here would intersect with this 0 line down here, so the function being equal to 0. But we can easily make a function that doesn't intersect. So what's happening here? Well, the issue is that with certain combinations of A, B, and C, we get that this content within the square root becomes negative. And we then say we can't take the square root of something negative, so there is no solution. And that kind of feels okay in some sense, because we can see, well, it doesn't intersect, so I guess there's no solution. But on the other hand, you should have two solutions, right? It's a second order equation. There should be two solutions. So what's going on here? And what turns out to be the case is that if you just define a number, so you have an issue that square root of minus something pops up again and again. Well, if we define square root of minus 1 equal to I for imaginary number, and we just take that as another direction that numbers can take, that solves a lot of issues. And so this is the introduction to complex numbers. So a complex number is one that has a real part down on our normal number line here, and then it has an imaginary part. So it has I, 2i, and whatever is in between going upwards, and minus I, minus 2i, and whatever is in between going up and down here. So every number in this complex number system has two components, like a vector. And that's why we'll see later on with phase that we introduce what's called phasors, which means phase vector. So it's a vector mindset, but as we'll see later, phasors and vectors are not the same thing. Also, when you now have complex numbers as an input for a function, you can now also get that the function itself is complex. And therefore it can be a little tricky to plot all of that in one plot. If we do plot the function that we had before, but not with a real x input, but complex z, or c, I guess you call it, in the function, then suddenly we get this 2D span of the function. And I've tried to indicate here in a solid line the function that we had before, and then also that there really are two roots in this system, or this function. They're just hiding. We can't see them in using real numbers, but we can see them using complex numbers. And it will be shown later that polynomials are super important, because those transfer functions that I talked about before, they are typically what's called rational functions. So that's fractions where you have a polynomial in the numerator and a polynomial in the denominator. So those rational functions with polynomials are super important when it comes to characterizing signals and systems. So if you are unfamiliar with complex numbers, you might want to pause here and study some more. But let's carry on from here. So we have now complex numbers. They have two components, and we denote it as our real number plus I, and then the imaginary part here. We have our definition of I equal to square root 1. Anything else like square root minus 10 is just square root minus 1 times square root 10. So that factor can always just be taken out. This is the important part. And there are two ways we can write these complex numbers, as I said, this way of the real part and the imaginary part, and then also as a magnitude that would correspond to the length of a vector, and then a certain angle, and that's really just Pythagoras. And then in this final form, we see here it's the magnitude of the number itself, and then it's the angle, or what we will call the phase, because when we look at signals and systems, we typically call this angle phase. Then there are some rules that you need to know about complex numbers. They will be a little important later on, but not too important. When you add and subtract, it's easiest to keep it in this rectangular form here. It's just real plus imaginary, because like vectors, you can add up the real parts and on their own, and then the imaginary parts on their own. And if it's subtraction, you just subtract the real, and then you subtract the imaginary. If it's multiplication or division, it's better to go to this polar form here. And then it's just magnitude times magnitude, and then it's the face of one of them plus the face of another of the numbers. If it's division, it's this face minus this second face. So that is basically it for numbers, at least seen from our perspective. So let's try and move on to signal systems and fields. So we now define a phasor. That's basically a complex number. Sometimes it's called a complex amplitude of a signal, for example. Same thing, you have a magnitude, you have a certain angle or a certain phase, and you have a real part and an imaginary part. I've drawn here a unit circle, and that comes from Euler, who looked at this like in the 1700s, I think. So he established this relationship between the exponential to ix, so I is this imaginary square root minus 1 that we are carrying around, that it relates to cosine plus I sine x, and that will be very important later on. And also that the magnitude of these are just 1. So any complex number that falls upon this unit circle is written in this form, and it has a magnitude of 1. Then there's also Euler's identity, which we will use later on when we look at polarity. And that just states the specific case of entering pi in radians. So pi is over here. In Euler's formula, you do that and you get minus 1. So this phasor, if you rotate it all the way over here 180 degrees, then that is minus 1, as we can see. Yeah. Then for looking at signals and systems, we typically have a time variation, so a signal will vary over time. And so we expand here, and we have an angular frequency omega, we have time in general as t, and then we can have an additional phase on top of that. So that's really the starting phase, or the initial phase. And that's what we call the phasor phase, because that is how the phasor looks at t equal to 0. So phasor phase is the initial phase. And still, no matter what you enter here after the I, as long as what you enter doesn't have an I, then the magnitude is still 1. But now it can vary with time, so you can think of an initial phasor at t equals 0, and then a phasor that rotates with time. And with the definition we have here, it's going to rotate counterclockwise. So that might be a little counterintuitive, but that is how it is. And then, of course, we can scale this with an amplitude or magnitude, if you will. So the phasor doesn't have to reside on the unit circle. It could be anywhere. So we need an extra variable to handle that. And we write here that it is a function of omega. So for each frequency, there is a phasor. So if you have a system and you want to characterize that system over frequency, well, then there is a phaser for each frequency to characterize that system, as we'll see. And of course, now when you take the magnitude, it will be this amplitude on its own, or this magnitude. Yeah, so now we have our phasers established. But phasers are complex, and what we measure isn't complex typically. That's a real signal. And that is where we use phasers because it makes things easier to do calculations using phasers as opposed to real signals. I'm not going to show examples of that, but if you start using sine and cosine on their own, it becomes much more complicated than using this polar form here. So there are sort of two approaches you can take to this realization. So you can say, well, we know that this could be written, this phaser could be written as a cosine plus an I sine. So there's an imaginary sine signal attached to this. But you could say, if we don't measure it, we don't really care about it. So all we need to look at is the real part of this phaser. So we do all of our calculations in the complex domain, and then in the very end, when we want to see what is it that we measure, we take the real part. So that's one approach. The other is, you could say, all we see is the real part, but the complex, the imaginary part is there. And that becomes a little bit philosophical. Which are you going to go with? But I hope with the examples that we show in the following, it will be clear at least that the complex approach has some advantages that the real approach does not. And I want to say very clearly now that this phase here, this phi, that is what counts. I see way too many blog posts and forum posts where people talk about this omega t and put some relevance to omega t as explaining things about phase. No, this is the phase that counts, this phaser phase, this initial phase. That is what you plot if you have a frequency response of whatever, a loudspeaker. That phase that you plot there is the phaser phase. It has nothing to do with omega t. The fact that omega t is there is fairly irrelevant, because if you have an input and an output, they're going to vary the same way with omega t. What you are after is this, the phaser phase of the system. That is the characteristic that we want to see. It is what gives us the temporal behavior also, as we'll see. So that's very important to understand that. That also means that this view that I sometimes see depicted, that needs to go. This idea about you have zero phase here, you have 90, 180. No, that's not a good way to think about it. And one way to show that is to imagine a cosine instead of a sine. So you start up here at 1 and then it varies. You would still write 0 and 90 and 180. So there isn't any difference between these signals. So what all you're showing here is that at this point in time, omega t is 0. And at this point in time, omega t is 90 degrees. That's not relevant, really. That doesn't tell us anything about the phase of a signal. So let's look at what is the phase of a sine signal. So one way to approach this is to say, well, we know what a sine signal looks like. It starts in 0 and then it goes upwards first. It has a magnitude of 1, and in this case, omega is 2 pi, just some arbitrary number. And then we say, from a phasor view, we're interested in having the real part describe our real signal. And the real part was best expressed using a cosine. So we transform this sine omega t into cosine omega t minus 90 degrees. And you can just look that up. And that gives us our phasor phase of minus 90 degrees. You can test that by putting a phasor, as we have down here, a phasor that points downwards minus 90 degrees at t equal to 0. And then look at the projection onto the real axis. So we have the real axis here. We have a phasor that points downwards. So the projection back onto the real part is 0. It has no component. It has no real component. It has a purely imaginary component at t equal to 0. That's what we have over here on the left. It starts out as being 0. And then as it rotates, or the phasor with time in it rotates, then there will be a later point here after a quarter of the full period where the projection onto the real part is 0.707, for example. And that is what we have over here on our sine. And you can do that along the entire sine signal. And then hopefully you can convince yourself that a pure sine with no added phase here, it really has a phasor phase of minus 90. And that's what you'll see if you look up what is the Fourier transform of a sine. You'll get these minus 90. I have a little more detail on the next slide about that. But now you can do it for other sine and cosine with some arbitrary phase. Here I start out with a cosine just to make it a little easier. I have my omega t that I always carry with me, and then I have minus 45 degrees as my phasor phase. And again, you can test this. So at t equal to 0, our phasor is minus 45 degrees down here. It projects onto the real axis with 0.707. That's what we have here when we plot a cosine omega t minus 45 degrees. And then at a later point, it will be completely on the real number line here. So it has its length of 1, so the real part is 1. And that's what we see up here. So again, everything checks out. This signal has a phasor phase of minus 45 degrees. There is a detail, though, that we should tackle now, and that is that if you say that it's not just that I see a real signal and I ignore the imaginary part, all there is a real signal. If you somehow define that, and you can do that in signal processing, then you need to get rid of that imaginary part that we see, that we project onto the imaginary axis also. And the way to get rid of this is to introduce what's called negative frequencies, which sounds weird, but really, as soon as you start talking about frequency, you have made some abstraction in your head already, even if you don't recognize it. So positive and negative frequencies, it's still abstractions that fall out of your calculations, because really all there is this signal that varies with time. It's our analysis that introduces frequency to this. So the way to get around this issue with having an imaginary part and being able to define a completely real signal is to introduce a second phasor. This phasor has half the length of what we saw before, and it rotates the other way of the phasor that we introduced that rotates counterclockwise. So now instead we have two phasers. They have each half a length of what we had before. So in this case 0.5 in I should say magnitude, not length. They have 1/2 as magnitude. And then they are positioned in this way, minus 45 degrees as we saw before, and then 45 degrees. And then they are summed. So the sum resides here on the real axis. And there is no imaginary part, because the projection from one phaser is cancelled out by the projection from the other phaser onto the imaginary axis. But the real part stays the same. So you can imagine this phaser here rotating this way, this one rotating this way. And if you do the analysis, you can see you get the same thing as before. So negative frequencies, while it sounds strange, are needed if you define that your signal is purely real. And it becomes even more important when looking at systems where you can have a system that you for sure know is real, and therefore you need to consider these negative frequencies. As these phasers just rotate around, we get some kind of sinusoidal output. And that means these phasers are meant for steady state. It's not meant for something that cannot be described via sinusoidal signal. We'll see later with Laplace that we can imagine phasers that rotate with a certain frequency, and then they kind of spiral. They get smaller and smaller and smaller, or they get larger and larger and larger. So you can imagine phasers describing like an exponentially dampened sinusoid. But think of it as steady state, something that has been going on for a while, and now your output is just some kind of sinusoidal. There's no transient behavior. Perhaps even for signals, they are very often acausal or non-causal, meaning they have started before time. They've just been going on forever. So that's steady state for a system. A steady state situation means that you have had whatever transient behavior in the beginning, and now the system has settled. And also, it's one frequency at a time. So for each frequency, you have a phaser or two phasers if you have real signals. That also means that it doesn't make sense to compare a phaser at one frequency with a phaser at another frequency, and comparing those two phases that they have. You need to look at that on a frequency response characteristics, that you plot the phase as a function of frequency. And also phasers are used for signals and systems, and something like impedance, for example, that's another steady state property. So impedance will also be described via a magnitude and a phase, and you can have whatever input and output variables. It could be a voltage input and a displacement output or something. If it's steady state sinusoidal, you can describe it via a phasor, and you should. Real signals require negative frequencies, and so do real systems, and we'll get to that. One thing you can do, this is not really important for what we're talking about, but you can add up phasers at different frequencies. So in a harmonic sense, where you have this harmonic distribution of frequencies, and then you have them rotate around in time, positive and negative frequencies, and you can look into Fourier transform in a discrete domain, And you'll see that you can use phasors for plotting symbols. So you're kind of going the other way of what you usually do with these transforms. But that's just a little detail. So one issue with working with phasors or working with complex numbers, you could say, is that when you choose to work with magnitude and phase instead of real and imaginary numbers, there are some issues typically with phase. There is some ambiguity typically to consider. And I think this book that I mentioned before by Stephen Smith covers most, if not all, of those issues. So one thing is, how are you measuring your phase or your angle? Is it radians? Is it degree? What is it? You can have issues where you divide by 0. We saw that the angle is really a calculation where you have a fraction. So you can have issues with dividing by 0. Oftentimes this arc tangent that you need to calculate comes in different versions. It could be called A-tan or A-tan2 or something, depending on which quadrant this phase or this phasor resides in. Some issues with that. You can have that the phase fluctuates greatly with small magnitude. So if you have very, very small real and imaginary numbers, but one is like 10 times, let's say the real part is 10 times larger than the imaginary part, well, then the phase will go towards 0 or some low number. But if it's all noise, then at the next instance or at the next frequency, it could be the other way around. Maybe now the imaginary part is 100 times larger. So you can have these weird phase fluctuations when the magnitude is not very big. And then there's some repeatability, or this 2-pi ambiguity, where you can rotate a phasor 2-pi and you're back to where you started. So looking at just one frequency, you can't really see how many added turns have this phasor had. And that's why it's good to look at the entire frequency range, because there you can see how quickly the phase sort of unwraps itself. That's another thing. I'm not sure it's mentioned here actually, but when you plot phase, you can do it wrapped or unwrapped. So you can say, I want to stay between minus pi and pi, so that the phase, whenever it reaches one of those endpoints, it has to wrap to the other one. Yeah, so there are different issues with this, and we'll see later on that it truly is an issue, but we'll try and cover it. Yeah. Okay, so the reason that it's called signal systems and fields and not signals and systems like most books or chapters are called is that when looking at this on YouTube videos, for example, which is not always a good place to look, you'll very often see people jump straight into waves to explain things about phase, or they say they look at waves, but they're looking at signals. So I just picked an example here where it says square wave, sawtooth wave, but what she's looking at is Fourier series and Fourier transform. So this is not a wave, this is a signal. And I think that is a you have to distinguish between signals and waves in order not to confuse yourself. So a signal can have magnitude and phase, there's a certain period, and as we'll see later, there are certain delays that you have. When you have a field, you can have waves. You don't always have waves in fields, but here I mean really fields with waves. And there you have things like you have propagation, you have waves and wavelengths, phase velocity, group velocity. And that's fine, but I think you should wait with that until it's needed and not start confusing waves and signals. Yeah, as I said. It's not that there's anything wrong with waves. It's certainly a big part of what I do in my work, but it's important to know the difference. And if you animate something, that's another thing I see in these videos. These signals are animated, but really there isn't anything to animate, because at each time you can only have one number for that signal. So it's not that variation can be animated, but you can animate a wave like this, and then you can extract like pressure, power, whatever, and then you get a plot for that. And it could be, in this case, it's frequency. It could be a time signal, but again, that time signal you wouldn't animate. That would just be a plot as a function of time. And I can see that it leads to confusion, not being aware of this wave versus signal issue. So just to get rid of or tackle it now, let's look at a wave and see what's going on. And so what's going on is that I'm looking at a very simple case here, where it's pure 1D propagation. So I have an x-axis, and I have a wave in a tube or whatever, and it's traveling down here. So there's a certain propagation speed and things like that. So the way to add it into a signal, which we can do in this case, is to subtract this term here, k times x. So k is the wave number, it's omega, so the angular frequency, divided by the propagation speed. So the speed of sound in this case. So there is an added term, and I think that term sometimes confuses people also. That's why I say drop looking at waves for now. For acoustics like I'm looking at here, all frequencies have the same propagation speed. So there's only one number, c, to consider here. So what you can do is, instead of having this distance, you could say x, you can convert that into a delay instead, as I've done here. So minus omega t, big T here, that's the characteristics of a time delay. That's how you include a time delay, as we'll see later on. So if you were to plot this as a function of angular frequency, you would have something that goes downwards with omega minus t as your slope. And then you could really absorb this and say, well, then my total phasor phase in this case would depend on where I take out the signal. But wherever I do, I could subtract this term here, and then I would get my phasor phase. And this is where I say, wait with that until you get the first parts here in order. But this is how you would do it for a 1D case. Okay, I think we've handled what I've listed here, so let's move on to transfer functions. So transfer functions are about system behavior. You have typically one input and one output that you're interested in. It's very often introduced in electronics classes or electrical engineering. So my background was that I started out in EE, so electrical engineering. So looking at transfer functions and phase and complex numbers, that was such a big deal of what we did at the time that I just do it automatically these days. But I can see a lot of engineers that maybe have gone more a pure acoustics route or pure structural mechanics. They are not that well versed in signal processing, which can be an issue. But the systems that we're looking at are called LTI systems. So they're linear, meaning that superposition holds. And then they're time invariant. And as we'll talk about loudspeakers later on, maybe we should say that the typical loudspeaker really isn't linear, and it really isn't time invariant either. But for what we're looking at, we can certainly assume that that's going to be fine for what we're looking at. Yeah, so it's typically as I write here, single input, single output systems. So it could be a lumped representation of a loudspeaker, for example, as we have here. And typical input could be a voltage. So this voltage would be described via a phasor, a voltage phasor. It has a magnitude and it has a phase. And then we are interested in some kind of output. It could be the displacement of the cone, for example. So in this circuit, the current here would relate to velocity. But let's say we're interested in something that could be derived from velocity, in this case, displacement, or the other way around. In this case, you could simplify the system if you wanted to. And this is just to illustrate how we get to the transfer function. So you could simplify the system and say, my loudspeaker is described via a mass and a spring and a damper, which is not too far off, actually. So we have this 1 degree of freedom system, and we have a force that we apply to that system. And then we have a force balance equation here. We have our external force, and then we have how the individual components react to that force. So it states that mass times acceleration plus this resistance times velocity plus the spring stiffness times the displacement all add up to the applied force. So this is a very typical situation where we have what's called an ODE, so an ordinary differential equation. And so many systems that we work with in our day-to-day life can be described via a differential equation. Sorry. Without going into too much detail, we typically transform from our time domain with differential equations into some kind of frequency domain. It could be via a Fourier transform, or it could be via a Laplace transform. Typically, when we work with transfer functions, we keep it Laplace, which is more general. And so, as we'll see on one of the next slides, one reason for doing that is that these differential equations turn into those polynomial equations that I was talking about. It becomes much easier. Instead of differentiating twice, we multiply by s twice. And s is just a complex frequency. So doing this makes life easier, but you need to study what the transform is actually doing. If you set it up with this Laplace approach, you can now rearrange terms. And what we were after in the first place was how much displacement do we get for an applied force. So x divided by f. But here we are in the Laplace domain. So we have our Laplace frequency or complex frequency here. So omega is still our angular frequency. The I is the square root of -1. And then we have another coefficient here which tells us how much damping we have. And it's better to see that visualized. So hang on. And we see that when we take the previous equation and rearrange it into this transfer function that we denote h, we get a particular form. And we can see we have s squared down here plus something s plus something. And then we have the same something up here and a factor. And what we have here is a low pass filter function, you could say. There's a certain gain that tells us how much amplification do you have at low frequencies. And all of the system behavior is inside this transfer function. This is all we need to know. Also, it makes sense because if you plot the frequency response of a low pass filter, it's flat and then it goes downwards. And what creates sound from a loudspeaker, or what will create a flat pressure, is a flat acceleration, as we've talked about in previous videos. And you get a flat amplitude, or you get a flat acceleration if you have a displacement that has this form. So that checks out. And again, your input is now put in a phasor form. In this case, we kind of go from Laplace to Fourier. So we are now ignoring this part of the frequency, the complex frequency, and this is really to go to pure sine signals, whereas Laplace also includes these damped or exponentially increasing sinusoids. For our purpose, we are typically only interested, in the end at least, to look at these pure sinusoids, because any relevant signal that we want to look at, like a music signal, can be decomposed into these pure sine signals. So our displacement output is a phasor, our force input is a phasor. They have complex values, one for each frequency. And our transfer function has complex values. So our transfer function has a complex magnitude, and it has it has a magnitude, and it also has a phase. And that phase of the transfer function is the output phase minus the input phase. And this is why I say this omega t that we carry around is not really important, because that's going to cancel out anyway, because it's carried on the output as well as the input. So it's this phasor phase that is important. So this phasor phase for the transfer function tells us how much is the output phase change for a given input phase. So the difference has to be what is the system doing to the output. Yeah, so again, this is complicated if you don't know about Fourier and Laplace. So you're gonna have to trust me on this one, but it is much easier to map into a complex frequency domain like Fourier or Laplace, because it takes us from these integral differential equations where we have to integrate or differentiate, which is a bit tedious to do these calculations, into having these polynomial rational functions where we have fractions of polynomials. It's pure algebra. It's much easier to deal with. You get rid of convolution. All students hate convolution, and instead you get multiplication. And also the transfer function, when you plot it, as we'll see in one of the next slides, it gives you directly the steady state response just by looking at it. And transient behavior is held within the transfer function, but you need to do some calculations to see what the what the transient behavior is, but it is contained within the transfer function. So as we talked about, when we have a complex input, we typically also have a complex output. So in this case, S would be our complex input, the complex frequency, and then we want to see how does the system behave for these complex frequencies that we input. And since the transfer function is complex, it also has two parts. So you can plot it, I haven't plotted here, but I just illustrated that you can plot it as a real or an imaginary part, or the much more typical one is to look at the magnitude of the transfer function and then the phase of the transfer function. And I've done that, but for another system, because I want to use this system throughout. And the system I'm using is what's called an all-pass system. An all-pass system has a magnitude of 1, or at least a constant at all frequencies, but I should say for all sinusoidal frequencies, so pure sinusoidal frequencies. So it has a complex input and a complex output. There's also what's called a region of convergence. You can see I have these mountains here where I have these green dots, but you can perhaps make out that half of the mountain, so sort of what comes behind here, has been cut off. And that's because I'm plotting within the region of convergence. And I know what it is because aside from a transfer function, I also know or assume that it's a causal system, meaning there is no output before there is an input. So typically we state that there's a certain time t equal to 0 from where we look, and whatever happened before that is not important. So the typical physical systems that we are looking at are causal, hopefully, that nothing is coming out of the system before we send it in. And so really a transfer function is not quite enough to completely characterize a system, but we tend to forget it because the only other thing we need to know is that it's causal in order to truly characterize our system. But it's so trivial that it's almost always a causal system that we're looking at. So over here I've plotted the in dB the magnitude. So it's really 20 times log 10 to the magnitude of this transfer function. This transfer function has a second order polynomial on top here and on the bottom, so the denominator. The only thing is that there is a minus sign here, so we can probably imagine when we solve this system it will have different roots or different solutions. And so why is that important? We're not solving anything equal to 0. No, but for certain frequencies or complex frequencies S, this will tend towards 0. And so that's why we think of it as where is this 0 and where is this 0. That will be very important for how the system behaves. And we can see that we have these large dips for certain frequencies. So think left, right here is frequency, our typical frequency. And then sort of up, down, or what should we say, depth-wise, we have this dampening term in our Laplace S. So for those S's, so that's the values that we have down here. For those S's where all of this goes to 0, we have these dips that tend towards minus infinity. And that's why I've indicated, or what I've indicated here in yellow, that these dips refer to our numerator here. For other s's, this term here will tend towards 0. And so the entire transfer function will tend towards infinity. And that's what I've indicated here. So we call these mountains here the poles. So we have 2 poles. And these dips we call the zeros of the system. So a system has poles and zeros, and they completely characterize the system. Now what's interesting about a all-pass filter is that there's a balance, so that you can imagine a tightrope here right in the middle. And that's where this term here is 0. That means if you're only looking at pure sinusoidal waves, nothing is exponentially decreasing or increasing. Pure sine, steady state, it's been going on for a long time. Then you can see for each of these frequencies along this line, higher and higher frequencies up here, negative frequencies going to the left, the system will not change its amplitude output. It will just give you the same amplitude out as you put in. And that's the characteristics of an all-pass filter or all-pass system. But if you go anywhere off this path, you won't get that anymore. That means that there are signals like an exponentially decreasing sinusoid, for example, where you won't have this system behavior because you're somewhere else on the transfer function. Not too important for what we're doing because we are looking at these sinusoids. But I think this visual is very important for seeing how the poles and the zeros warp this surface and how that will determine the output. And one thing you could imagine is having a system where you have, let's say, a pole on its own. So we have this mountain, and then you make changes to the system so that this mountain becomes closer and closer to your omega axis. And you can imagine how the omega axis level here is gonna be increased. You're gonna get, you're gonna follow a line that increases as the mountain comes closer to your omega line. So I think that's a good way of thinking about transfer functions. Another thing to take from this view is that imagine you look at it from up top here and you just look down on it. Then you would get this view. So now you have your omega line up down, and typically you would plot a cross for a pole and then a circle for 0. So sometimes this is all you get visualized, which is enough, but I think this picture here is better. But it's the same thing. And also what you now can do, having this transfer function, is to imagine that you just take a slice right down the middle here. And that is going to give you this plot here in the middle. So it's 20 log 10 to the transfer function with pure sinusoidal frequency. And so that's where you get this flat line. So the magnitude response is just for this system 0 dB. It's going to give you whatever output magnitude that your input has. But again, you're just looking at this view from different angles. I think that's important to realize. There is, of course, also a phase that you could plot. You could also plot a real and imaginary. That's typically not done. But there also is a phase, and here you have to be a little careful when plotting it, because you now have to do this wrapping and unwrapping. But I think you can make out with this solid line here the phase of the of the transfer function for sinusoids. That what I just plotted it myself by hand. I hope it looks like this. And I should have plotted it also for negative frequencies as we have here. But that's the phase of our transfer function. And now we can proceed and cut away the negative frequencies like I've done here. So why can we do that? We see that we have negative and positive frequencies. Well, the thing is that the systems that we're looking at are real, meaning physically realizable. And those types of systems have this symmetry that we see here, that one pole is the mirror image of another pole. So at positive frequency, we have a pole, and at the same negative frequency, we have a pole. And this conjugate symmetry we are almost always going to have because we look at real systems. So we can just say, we can look at one side of the spectrum, and then we know that, yes, we will be carrying around an imaginary part, but we choose to ignore that. So this is the typical view that you will have in an electronics book, where it's probably never mentioned that there are negative frequencies, whereas in a signal processing book, you're going to have mention of negative frequencies. And that can be a little confusing as to why you can ignore it in one case. But that comes from looking at real systems. So what could disrupt this? Well, if you had a system where someone told you that the mass is not 1 kilogram, but the mass is 1 plus I 2 kilograms or something, then you wouldn't have this symmetry, and you wouldn't have a real system. It wouldn't be physically realizable. But there's nothing stopping you from making a model like that. So just be careful if you do that. So we choose to look at just one side of the spectrum. And then also, instead of writing I omega, we typically just carry around omega or even F. So F is frequency, and 2 times pi times F is the angular frequency, omega. Really, we should be writing always IF or I omega. But in engineering, or really anywhere else, we just ignore it and say, yeah, we know the underlying mathematics. We don't want to carry this around. But if we were really, really strict, we would carry this I around. Again, this is for steady state systems, but you can look directly at the transfer function and the plot we saw before. And for sinusoids, even if they're exponentially damped or increasing, you can just find that complex frequency, look down on the plot, this 2D plot, and say, how will my system react to an input at this frequency? And that's what we have here for our purely sinusoid frequencies. So it has a flat output magnitude-wise, and it has some arbitrary phase. There's no requirements for what kind of phase an all-pass system should have. So here is the structure that you typically have some kind of lumped element circuit. And then you find the corresponding transfer function. You can plot it if you want to. That gives you some insight. Then you take a slice. You just look at pure sine signals, and then you ignore negative frequencies. So if you do a measurement, that's what you're going to jump to directly. You're not going to see any of the details about transfer function. You're just going to get the frequency response, so magnitude and phase. And typically that's enough. Also, one thing to note is that, especially if you're doing simulations, you are the one choosing the phasor reference. You're the one who's inputting the inputs, like voltage or acceleration, whatever it is. If you enter a 1 without thinking about it, you're probably gonna do fine. But really try and think about it as a phasor that you have input now. By putting in a number of 1, you have chosen that the phasor phase is 0. You could enter a number and a phase, so the magnitude and a phase, or a real number and an imaginary number, and that would be the phasor for that input. So if you have multiple inputs, like maybe you have a displacement, but you also have a voltage, it's up to you to make sure that they have the correct phases for what you are doing. You are determining the reference that you're referencing back to when you look at an output. So if you have a voltage input of 2.84 or whatever, then that phasor has an angle of 0. So when you get an output, like a pressure output, and that has a phase, that phase relates back to that pressure phasor. So if you change that phasor phase on the input, the output phasor phase is gonna also change in correspondence to that. So the system stays the same, because if you subtract the two phases, the input and output, you're still gonna get the system phase correctly. But just try and think about that you're in control of these phasors typically. Right. So we haven't really gotten to loudspeakers yet, but we're edging into crossovers, I would say, because a lot of times crossovers are called like phase coherent or time coherent. It's not always clear what people mean by that. What I would say is that there's what you can call transient perfect in RF, so radio frequency and transmission line modeling. We talk about distortion-free or distortionless transmission. And that is something that will give you a transient perfect output. So whatever weird signal you're gonna send in, you're gonna see that replicated somehow without being too distorted. So it has no magnitude distortion, meaning that it has to be a flat magnitude like the all-pass system that we saw. But also it needs to have a very particular phase, and that is the phase relating to a delay, as we saw earlier. And so the total transfer function that such a system must have is what we have here, k to times exponential minus I omega, and then the time delay. That is what is going to give us an output that is only scaled in magnitude, the same at all frequencies, and then it's delayed. That's what we call distortion less or distortion-free transmission. That means that if we have our input in green, then something that would be accepted as distortionless could be the orange one here. It's been scaled up in frequency, but it is perfectly a scaled version and time delayed version of our input. So one thing to note is that in some books they accept k as being negative, meaning they accept that there is a sign flip. So this dashed output would also be considered distortionless. And I am in that camp. That is how I view it, because as we'll see later on, what that really is, this sign flip is a polarity flip. And that is such a benign thing to do. It's so easily correctable that I would say this is also distortionless. I'll get into more details about that, but just note that there are these two different ways of looking at it. This is important. When I say distortion in this case, I'm talking about linear distortion. So something that changes the magnitude, which would be if this magnitude response is not flat, it wiggles and whatever, that is considered distortion of the magnitude, but it's a linear thing. Superposition still holds, everything scales, but your output is going to look different from your input. You can't scale it and time delay it back to what your input was. And the same thing goes for phase distortion. Anything that isn't a flat phase sloping downward starting in 0, like this plotted on a linear frequency scale, that is going to be considered phase distortion if this phase is nonlinear and it wiggles. And so that's not to be confused with nonlinear distortion. And oftentimes when we say distortion, we really mean nonlinear distortion. And that could be like geometric and material nonlinearities, where you would perhaps get an output where you have multiple frequencies, but you only input one frequency, something like that. We're not going to talk about nonlinear distortion here. So it's just that the magnitude has to be flat, the phase has to look like this, or with a sign shift, as we'll see later on. A phase that could also be acceptable is a phase that starts out in minus 180 degrees or plus 180 degrees and then goes in a similar slope. And we'll look at that later on. And again, the all-pass system that we looked at before has a flat magnitude response, arbitrary phase. And then there's what's called constant voltage. And I take that name from some old AES papers that I used to read a lot when I was more interested in crossover design. And here you have like a system that works as a perfect wire, you could say, or the only thing it can do is change the magnitude. So you can think of it as a wire that also has a magnitude. So the reason I want to point out this special case is that when we look at crossovers later on, this is one of the cases we can look at. This is sort of the reference, or what some manufacturers tried to reach with their first order filters, but let's not get ahead of ourselves. So this constant voltage is a special case of all pass, and we can see that because any phase is acceptable for all pass. So if it's just 0, then it also falls under the category of all pass. And it's also a special case of linear phase, because it is linear and it just is 0 and that's it, but it's still linear. And then, all right, it's also minimum phase, and we'll get to what that means. We'll get to it now. So minimum phase and non-minimum phase systems, what is that all about? And really that's why I'm introducing these all-pass filters where the magnitude is just flat, because it takes us to the essence of what we're trying to look at, which is phase. So if the magnitude is always flat, then some of these terms become a little easier to understand. But minimum phase really means that the phase that you have is predictable from the magnitude. When I say predictable, it means you can calculate it via what's called a Hilbert transform. We'll not look at that. But if it is a minimum phase system and you know the magnitude, then you can calculate the phase from the magnitude. Also, conversely, if you know the phase and you know it's a minimum phase system, you can calculate the magnitude to within a scale. So you don't exactly know this K, but you know the shape of the magnitude at least. But typically we look the other way. Can we calculate the phase from the magnitude? And here, if you want to study things, it's something like Hilbert transform. There's some good papers on Kramer's chronic relations that explains in much more detail. But to any magnitude, there is a phase that is sort of its natural phase, you could say. It's minimum phase that you can calculate. If it doesn't have that phase, if it has more phase change than that, then that added phase or extra phase we call excess phase. So if you have a system and you somehow figure out, perhaps you have a measurement system and it tells you there's excess phase, you measure excess phase, it means that that phase is not minimum phase, or that system is not minimum phase, because the magnitude doesn't match the phase. So we'll look at some of the consequences of that. One consequence of having a minimum phase system also means that you have the minimum amount of phase lag and group lag in the system. And we'll get to these lags or time delays later on. So what could... there's actually one thing here. So very often there's some kind of definition in your signal processing book about minimum phase systems. And when you take the course, it might not be really clear what they're talking about. But the statement is something like, for a stable causal minimum phase system, there exists a stable and causal inverse system. So what's that about? So in this case, you are trying to find an sort of an equalization system or inverse system that can undo what your original system did and take you back to the system of a wire. So a transfer function that's just one. So it's easy enough to calculate because the inverted transfer function is just 1 divided by the original. But what is problematic can be two things, because it says here the inverted system has to be stable and causal. So if we take causal first, imagine you do have a original system, but it's a system that is a pure delay, like we have here. So flat magnitude, and then a straight line for the phase, and straight line in linear scale, very important. How are you gonna make the inverse of that? Because you've delayed something, and now you wanna get it back to where it was. The only way to do that is to look into the future, because now you need a negative time delay to offset that positive time delay that you have from your original system. And that is not going to give you a causal system, meaning you will have something that looks into the future. So it doesn't have a causal correspondence between output and input. It would need to output things in advance to counter the original system, but you don't know what you're sending in to the original system. So there is no causal inverse system that you can come up with. It has to be acausal or non-causal. So a pure time delay would be problematic when it comes to the causal inverse. Also, one thing to note is, and we'll get to this later, this is what I mean by we have to skip a little back and forth between things, but a minimum phase system cannot have any latency. And I'll give my definition of latency later on, because we know that a minimum phase system will have a causal inverse. And so if we can, if the minimum phase system had a delay, we wouldn't be able to find a causal inverse. And we know we have to be able to do that. Otherwise it will be a non-minimum phase. But it can have phase delay and group delay, and that can be somewhat confusing. But we can undo the effect of a minimum phase system, meaning it needs that inverse will be causal. So the minimum phase system is not delaying anything as such. There's no latency in the system. I think this will be easier to see later on. So what's the other issue that you can have when trying to find an inverse for a system? Well, when you have these series or cascaded transfer functions like this, you multiply the magnitudes and then you add the phases. But sort of more schematically, you can think of it as dropping the inverted, the poles and zeros from the inverted system are sort of dropped upon the original poles and zeros. And that you can do for any system. It doesn't have to be the inverse of the original. As long as they're in this cascaded setup, you can think of it as sort of dropping all of the poles and zeros on top of each other. And a pole and a zero at the same frequency will cancel out. So the approach to inverting the original system that we have here is to add zeros where we have poles and to add poles where we have zeros. And so that works in theory because this will give us a transfer function in total of just one. It's going to be a flat surface that we look at. We've canceled everything out. But it's problematic because this inverted filter here now has poles in this right-hand side of the complex frequency domain. And we can't have that when we have these causal systems, because it means that the system is unstable. So we can have non-minimum phase systems that don't have a stable inverse, and we can have non-minimum phase systems that don't have a causal inverse. But minimum phase systems do have a stable and causal inverse system. Yeah, just a note here, because I've seen this mentioned also in some forums, that you can of course still try an EQ like with the parametric EQ, where you have a center frequency that you can vary and a Q. And if it's a minimum phase, let's say you have a peak in a magnitude response. If that peak is a minimum phase system, comes from a minimum phase system, you can use this EQ and get a completely flat response. You can undo this peak with a dip. But if it's a non-minimum phase peak of sorts, you can probably still EQ that to some degree, but the phase is gonna be off. So it's not that it's completely impossible to do anything about a peak or a dip, but it's just formally you cannot completely undo that effect if it's a non-minimum phase system. And then there's another option that with DSP, you can go for this transient perfect linear phase at the expense of having an overall latency in the system. So instead of going for a minimum phase, completely flat magnitude response with a minimum phase, which would then be 0, it would be close to that of a wire if we had infinite bandwidth at least. But with DSP, you can still obtain this inversion if you're willing to have a latency in the system, and you could maybe think of it as taking in enough samples so that you can predict the future. That's the simplest way I can say it. That the issue with causality is gone because you can just wait and take in enough samples, and then you have what you need to predict the future in some sense, because you can just make a new timeline. And we'll have a very brief look later on this. I thought I would include another example here. So instead of inverting completely to a wire, a transfer function equal to 1, maybe, well, that's not what we are always going for. Something that you could think of is just to manipulate the output somewhat of a system. So I took one example here that I found interesting, this Lindquist-Greiner transform, where you have some kind of response from a driver, so a loudspeaker driver in blue here. It has a certain characteristic frequency and a little bump here, so maybe you feel the Q is too high. Here you can take the same approach of thinking of just sort of dropping poles and zeros on top of the original system. So the original system is described via this second order high pass function. And you're not happy with the poles. The poles are what determine this Q and this characteristic frequency for the original system. So very simply, you can just say the way to get rid of them is to have them as zeros. So whatever you have down here, you put up here in your EQ system, and then you define new poles that give you the response that you're looking for. So the total response is the numerator from this part and the denominator from this part. So again, in blue you have some original poles, you drop some zeros on top of that, and then you implement some new poles. And that is what this Lindquist transform system does. So finding the transfer function is fairly simple. I imagine it took some work to figure out the way to implement it in this active circuit. So the circuit here is what's called a multiple feedback setup with this single operational amplifier. When you do it like that, you get a sign flip or polarity flip, as we'll see. And so you might want to get rid of that by crossing some wires. I thought about doing this with a cell and key or state variable, but I didn't do it. You can do it if you want to try it. That could be a way to get rid of this sign change, but also I imagine there's a high sensitivity on these components. The more components you add to one operational amplifier, the more each component has to do with multiple things. Like if you're just one component, it might change both the Q and the characteristic frequency. So you have a higher sensitivity when it comes to the available components and also the tolerance on these components. But that's another topic. One thing I was thinking when looking at this is perhaps you could use this circuit sort of the other way around, not to push the frequency down, but to push it up. So you could use it to a tweeter. I don't know what roll off of a treater is, or the characteristic frequency. Let's say it's 1500, and you would like to have a crossover that has a frequency of 2.5 or something, 2.5 kilohertz. You could use this transform, perhaps, I haven't thought too much about it, to push the response upwards so that it's higher in frequency. You could have it have a Q of 0.7, for example, and then you could add on top of that a second order Butterworth filter, which also has a Q of 0.7, and in total you would get a fourth order Lindquist-Riley. So that could be a way to, instead of trying to work with the treater as is and have some kind of crossover work for that, you could use this circuit to correct the poles that you have. Just an idea. Yeah, so minimum phase systems, I've seen some talk about all physical systems have to be minimum phase systems, and I don't quite know where that comes from, but it's not correct. You can have non-minimum phase systems, and yeah, there's some example I've seen a lot is this inverted pendulum, that if you want this pendulum to not drop all the way to the ground, but you want it to move to the right, you have to go left first so that you get this kink, and then you can follow sort of the fall of this pendulum with a correct velocity, and you can move this inverted pendulum, and that would constitute a non-minimum phase system. There's also this video here on how bikes work, where it's illustrated how in order to turn right on a bike, you have to turn a little left first and then right, otherwise you can't turn. And I put a car here with a, what's it called, a camper, a caravan, whatever. And that's sort of a classical example, even without this caravan. If you back up a car into a driveway, you first move a little bit away from the driveway before you come into it. So you have this kind of overshoot. And also if you add this caravan, you're going to have to turn the wheels opposite of what you otherwise would. And that's sort of as we'll see in a slide later on, that's a kind of characteristic of a non-minimum phase system, that it might not follow the input in the beginning, but then it starts tracking. So I think it's fairly well established that physical systems can have non-minimum phase characteristics. So that's something I see pop up often, that people say physical systems have to be minimum phase. They don't. Delay. This is probably the most dreaded one, because it's really not that well explained in a lot of textbooks or journal papers. I think people tend to forget that when they look at delay, they for sure have to define what is it that they're looking at, but also that when it all comes from, as we'll see later on, the delays come from looking at the phase. That's how a lot of these delays are calculated. This phase comes from a transfer function, and this transfer function is defined steady state wise. And sometimes that's not what you want for delay. And that's why I've put in what I call latency or transient delay. What I want to know sometimes is just when I input something, right as I input it, when do I get something on the output? And those other delays that we look at might not give me that information. So I write here, there isn't really stringency always in the literature and papers. You might see someone write that there is no phase in a minimum phase system. There is no delay in a minimum phase system, for example. And you have to be a little bit careful with how you interpret that. Which delay are we talking about? And I would say I couldn't find a paper or a book that gave me exactly this, what I wanted. So I had to look at this a lot on my own to finally find my way out of it. So at least what I present here is what I've settled on, and I might have to refine it somewhat, but I think it's fairly spot on. Let's see. So phase delay is defined as minus the phase at a certain frequency divided by that frequency, angular frequency, I should say. And this is what I often see people do on blog posts and other things, that they say a phase is just a time delay. And then they look at this phase delay and say, well, this is the delay I have in the system. That's the wrong way to go. You shouldn't say that phase is just a time delay. You can go the other way and say a pure time delay can be described via phase, but that's not the same. So phase delay, when you calculate it like this, is just the most naive way of calculating a delay that you can think of. This is just the apparent delay. So you look steady state. You find your for example, you look at one frequency. You find where does my input peak, where does my output peak, what is that phase difference, and then you calculate what is the pure time delay that the system could have, and then lead me to this view, steady state. That does not mean that this time delay is the overall latency of the system. It's just the apparent delay seen from a single sinusoid at that particular frequency. It's your best guess, you could say, at a frequency, if you at a delay, if you're told nothing else. So it could be, like I have here, that I have a dotted input and then I have a solid output. And then I have a delay of, a quarter period? No, a half period, right? So I have a delay of a half period. That's why I don't have any output for a while. And then I have it. It's a complete replica of my input, but it's shifted in time. So with phase delay, that is your assumption that whatever you measure steady state, so way after this transient behavior is done, you measure phase difference, and then you do this naive calculation. What would that time delay be? Which pure time delay would give me that phase difference? So that's a little dangerous approach. I think it's best in these cases just to look at phase. Because this would come into play like if you have a crossover and you have a different phase for the tweet output than for the mid output, but we'll look at that later on. There it's dangerous to say I have this time delay, because that time delay is not a physical time delay, it's just an apparent one. You could have a time delay coming from the offset of the two drivers not sitting in line, but that's a different thing. And then there's group delay, which really has to do with the envelope of a signal, and therefore I'm not going to go too much into it because I don't think it brings much insight into what's going on, because you need to look at a modulated signal or a group of signals and how they behave compared to the envelope of those signals. But again, it's an apparent thing that you look at, for example, you track this inner signal here and you say, where did that peak? You go down here and say, where did it peak on the output? You find this phase delay. You could do the same thing for this envelope and say, it peaked here, up here. Now it's the same envelope on top and on bottom. And then you have the same peak in the envelope here. And then you have a group delay. That group delay may or may not be equal to your phase delay. And that, I think, is better viewed directly from the phase and how it's defined. Because the phase delay is, as I said, just looking at the phase at a particular frequency, and then the frequency itself. And then you're imagining drawing a line from that. I can see I missed the point a little bit here, but if you just draw a line from the phase point here to 0, that slope of that line is going to give you the phase delay. So again, this naive approach, whereas the group delay tells you what is the slope in this point. What is the slope of my phase? Those two don't necessarily align, and they don't have to. And yeah, here's another way to look at it. If you're looking at these bursts or wavelets or something, it's important to look at the phase delay and group delay. And one thing that I see often is that group delay is described as sort of the true delay at each frequency. Sort of like the true inherent latency of the system. And then they plot the group delay, and it's typically like flat over a certain frequency range, and then it rolls off. It's true that the flatness of the group delay tells us something about the latency, but group delay in itself is not the latency of the system. And again, latency for me, so I'm thinking like video games or something like that. How quickly does something react? And this is what I mean with latency. At the transient, how quickly do I get something out of the system? That is not necessarily group delay, but it's often said so in literature. I think that's confusing. If you think back to looking at the slope and the phase, and then this curve or straight line, like phase delay, we can look at it again here. If you think back to this view here, and then imagine that the phase is just a straight line, then phase delay and group delay will align. They will be equal to each other. And that straight line will indicate that we have a pure delay in our system. And so it's natural to come up with what's called a differential delay. It's not something you see in books, but there's at least one AS paper where this is investigated, because if all you're concerned with is this distortionless transmission, then it's not so much about what is the actual number of the phase delay or the group delay. It's how similar are they to each other, because if they're completely similar, then you have a pure delay. And then if you have a pure delay, you have transmissionless, distortionless transmission. And that's fine. You can accept that. You can accept that delay. It's fine. It's probably not a big deal. And so what Leach was trying to define was how much of a differential delay, how much difference can I have between phase delay and group delay. I think he did it for amplifiers. Came up with some numbers. But I don't think that in general that this difference gives us anything physical. It's again not something where we can say, aha, now we know the latency of the system. It's just that the more these two coincide, the more we are close to having a pure delay. And if we do have a pure delay, then this is equal to 0, this difference. And that's what I have here illustrated, that if we have a straight line here, phase delay is equal to group delay, and we have a pure delay, a pure latency where we don't get an output for a while. When we have an input, it takes a while before we get an output. So if this differential is equal to 0 at all frequencies, we have a pure delay. Okay. I want to illustrate the problems that I see some people have with delay and with polarity in one go, really. And that is that they look steady state at everything. And they don't really think about how it came to be this steady state. So I'm showing you 3 situations here. I have this one scaled a little differently than these 2, but it says 1 here, so it is the same thing we're looking at. Dashed is or dotted is input sinusoid, and the output sinusoid is this dashed, solid line for all 3. And then I have this blue box that covers up something. And my question is then, how much can we say about this system or these systems if they are in fact different? We can say something. We know that the magnitude response has to be 1 because the magnitude is the same for the input and the output. We only know that for one frequency, and that's the frequency we're looking at. But at least we know that, so we can put a dot here in the magnitude. Also, we know the phase to within these 2 pi wraparounds, right? We don't know how many times it's wrapped around, but just looking at it, we would say there's a pi or minus pi difference, so 180 degrees, right? So pi or minus pi radians is 180 degrees, and we see that for all of them. So we know that they have to share these 2 characteristics. And we also know that we can calculate the phase delay just by knowing the phase in one frequency. So we can see it's that best guess at a delay is 1/2 of the period. But we don't know if that's the true delay of the system. But it's the phase delay. That's how it's defined. But if we take away the blue boxes, we see we have 3 quite different systems. If we start on the right, we have what I've shown on some previous slides, a pure time delay. So a time delay of half a period, at least for this frequency, it's half a period. And that delay is kept for all frequencies. So that delay you could calculate by knowing the frequency here, and then that would be the delay that you would see for all frequencies. So in that sense, you know everything by knowing this transfer function. This case, which looked the same, completely the same steady state, is a very different situation. Here we have a polarity flip, and we saw that polarity flip is a sign flip, so transfer function is -1, and we saw from Euler's identity that has to be a phase shift of pi or minus pi. So 180 degrees or minus 180 degrees. So looking naively, steady state, these two will look the same. And that's what I see a lot, that people talk about polarity, how it relates to a time delay, and they get confused because there can't be a time delay if you have polarity flip and all of that. Yeah, it's two different situations, so we'll get to that. The third situation here on the left is the transfer function that we started out with, this all-pass system. And here we see that in the very beginning that there's no latency. It gives us an output immediately, but it doesn't track the input, right? So it goes up and then it goes down. So when we say in signal processing that we work with linear systems, it means that we have one frequency in and we get the same frequency out. That is only correct to within a steady state condition. There can be transient behavior where you see a mode being excited, so you have a different frequency for a while, and then steady state comes into play. The system starts to realize, well, what is the force that is being applied here? I better comply to that. So when we say this thing about one frequency in, one frequency out, it only holds steady state. Transient, you can have more interesting behavior. But I've set it up in such a way that at that particular frequency we are looking at for these values in the polynomials, I also have this the same phase delay as for these. I have the same phase difference between the output and the input, and at this frequency it just happens to be 180 degrees. So I show this to illustrate how you can be fooled if you don't take into account transient behavior, because certain situations are going to look the same. And if you then conclude from there that they are the same, then you're bound to be confused. So if we again look at the system on the right here, it's a pure time delay. So phase delay, group delay, and the overall latency of the system are that's all the same number, and we already know that it has to be a straight line. So if we just know one point, we can just put that straight line straight to zero and then extend it. For the polarity flip, we have a flat line here. So it's just minus pi or pi, it doesn't matter, to characterize this -1 transfer function. The only way to do that, since the magnitude is the same, that the magnitude cannot take into account a sign change, it has to go into the phase. And that's what we see here, that it goes into the phase via minus pi or pi added or subtracted, whatever, to your original phase, which is in this case your input phase. So there's no group delay because the slope is 0. There's also no latency in the system. And now that can seem to not match what I said before, that if your phase delay and your group delay are the same, you can directly see your latency from that. So it looks like there's something wrong with the phase delay. But all that is wrong in some sense is that there is a sign change. If you flip this polarity back, you're gonna get a completely flat 0 phase for this system. So in that case, your phase delay is 0, your group delay is 0. Those two are the same. Their value is then the latency of 0. And so we see an issue with the polarity flip in a system in that it can obscure your view in some sense. And so you can get confused in your own analysis of systems if you don't take into account polarity flips along the way. I'll show one slide where I get into a little more detail. But you can have your phase delay and your group delay don't match up, but still they are very telling of your latency. True within a phase or polarity flip is what I wanted to say. For your all-pass system here on the left, you have a phase delay that is equal to the other phase delays because they have the same phase at this frequency. Then there's some group delay that I didn't calculate, but it will vary somewhat with frequency. And then the latency of this system, I think, is worth investigating because I think it will sort of put the nail in the coffin as to what is the difference between phase delay, group delay, and this latency that I'm talking about. First thing is, how did I even calculate, or how do I know the output? You could ask, how do I know these solid lines? Did I just plot them sort of by hand? No. For all of them, I calculated just to be absolutely sure. For the all-pass filter, I wouldn't know how to draw it. But the way to do it is to multiply whatever stimulus or input that you want to investigate, multiply that, and it has to be in a Laplace transform version, multiply that with the transfer function, and then you take the inverse Laplace of those two multiplied together, and that gives you this output. So I did that for all of them to be completely sure that the output was as expected. So in this case, I'm looking at a sine input, and that has a certain Laplace transform. You can build up more complicated input functions if you want to. You can typically find a Laplace transform still, but I'm not going to go into those details. Also, doing this inverse Laplace for simpler systems, you can do it by hand. It's tedious. You might need to do some partial fraction decomposition. So if you have MATLAB or Mathematica or something, I would highly recommend that to be sure that you've done the calculations right. But that's the general way of finding these outputs that I plot. Right, so let's try and look at the step response. That's something that you'll sometimes see in loudspeaker tests. I know Amir from Audio Science Review have just started showing them. I think it's a good idea to show them, although he doesn't think that they are very telling, because a lot of people think that phase is not too important for our subjective experience of loudspeaker. And I would probably tend to disagree in that if people say they can hear cables, for example, or differences between DA converters where it's very minute changes, if any change, and if you do a null test, like you compare the output from different cables or from using different cables, you'll probably not be able to hear any difference between one cable and the other. Whereas if you do the same for a loudspeaker where you have a certain phase and then you correct the phase somehow with DSP and you keep the magnitude the same, or the magnitude response, you will for sure have a difference in a null test because they are not handling transients the same way. So it's interesting this, for some effects, apparently measurements are not good enough and we have to trust our ears. For others, it's all about measurements, and I think the phase of loudspeakers is falling in between the cracks, and it's really super interesting for how the music signal actually behaves. So I don't know what that is about. Okay, so let's see how these three systems respond to a step. So a step is just something that starts from 0 and goes to 1 and then proceeds to be 1. So I don't show the input, but it would be up here. Again, we can start from the right. So the transfer function is a time delay, and we see that it is delayed, so the red curve here, but it perfectly tracks a very sharp step, and in that sense it is transient perfect, distortion free. It's just delayed. If we take the polarity flip and we accept a polarity flip as being transient perfect, within the realm of transient perfect, we can see that here we have no delay. It's just straight to -1, and then it keeps being -1. So it's a complete mirror version of or flip version of the input step. Again, I would call this transient perfect, but we'll get to polarity a little later. This more general all-pass system here is more interesting in some sense. So we can see that at first it shoots up. So that I think in loudspeaker lingo it's called the leading edge. So it tracks correctly, it goes upwards. But then you have this characteristic, like for these non-minimum phase systems, that they might go in the opposite direction than what you input, and it depends on how many zeros that you have in your right half plane. So you might have a system that doesn't go straight up, but it goes down before it goes up, if it has 1 0. I think that's how it works. So here we have 2 zeros, so it goes up but then down, and after a while it tracks the input. And you could say, well, what is the delay in this system? Depends on what you mean, right? Because there's no latency. It's just straight out of the gate. But you can also see that you could argue that it has the same delay as this pure delay. It sort of tracks a little bit the same, right? So it becomes a little bit difficult to define, or at least you should define delay before you talk about what it is. And that's where for this transfer function, we have different phase delays for each frequency, or varying phase delays and varying group delay. So there isn't, since the two are not equal to each other, there's no latency in the system, and at least for high frequencies we get straight out of the gate here. So you can think of this as whatever happens first is determined by the high frequency behavior of the transfer function. Whatever happens later on is more the slower low frequency part that comes into play. And you can also see that at high frequencies you're going to have something that's closing in on being just 1, so +1, meaning in some sense the polarity is correct in that it goes upwards for the leading edge. You can also see for low frequencies you again have something that tends towards 1, and that's also what we see, that it tracks the input correctly with the right sign at higher frequencies. So you can sort of view this transfer function, and if you get good at it, you can probably have some good idea as to how it's going to behave. But certainly the three systems behave differently. Yeah, so now we got to a slide that I mentioned several slides back, and that is that these non-minimum phase systems can have this characteristics of not tracking the output, at least in the beginning. So it might go up and down and then up again, or in this case, for a little simpler system, that it doesn't track correctly the input. I think the input here is a step, but the system has some filter. It's not an all pass. So you see this smoother curve. It doesn't shoot straight up. Some of the higher frequencies are cut away. And so there's a minimum phase transfer function, which is really just this one, but removing this minus s. That one goes up and follows the step to within what the magnitude response allows. That's really how you can think about a minimum phase system. It tracks the input to within what the magnitude allows it to do. And then you have a pure delay, and we see that in the green here that there's a certain delay, and then it tracks the response. I think it's delay times the minimum phase, otherwise it would shoot straight up. And then, yeah, the minimum phase one, where you have a 0 in the right hand plane, that one goes first down, no latency. It shoots down very from the get-go, and then it starts to follow the delayed version. And that's where you could say at low frequencies, yeah, it does have a delay, it does have a latency, but it doesn't have a latency seen from higher frequencies. And that is what I want to show now, because it can be confusing. So here we have the group delay and the phase delay as a function of frequency for this all-pass system that we have looked at before. It's typically easier to plot group delay than phase delay. For phase delay, you typically need to unwrap your phase and do certain manipulations to get to this. And perhaps that's why group delay is more often plotted. But we can see that they're not the same, group delay and phase delay in this case, but they do tend towards each other at lower and lower frequencies. So what I want to show is that as they get closer and closer to 0 for lower and lower frequencies, you do have something that looks like latency in the system, but it's not really. And I haven't ever seen a reference or a book or paper that goes into these details that we'll see now. So imagine that we are at omega equal to 1000. So that's a frequency of 159 hertz. So that's the dashed line I have here. There's a certain phase delay, there's a certain group delay. The two are not the same. There's a certain differential delay, the difference between the two. And then we input the sinusoid. At that frequency, we input a sinusoid. And we get exactly the same pictures on the left because it's the same thing we're doing. I just want to repeat here that there's clearly no latency in this system. The phase delay and the group delay are not the same at this frequency. So it just, yeah, it gives you some kind of output right away. Now, for a much lower frequency, like 10 radians per second angular frequency. And that's a frequency of 1.6 hertz. So it's outside of the plot that we have up here. So somewhere out here. This differential between phase delay and group delay tends more and more and more towards zero. And this is what I've never seen, and what I think is important. The two are very close to being the same. The value is 0.0028, and the response of this low frequency sinusoid is what we have here. So note that this says 0.15. So we are zooming in equivalent to what I'm showing here with an arrow or cursor. We're zooming in and we can see that it's almost flat. It's almost a pure delay for this amount of time before you get an output. But it's not a pure delay. That's the difference. You can look at the differential delay, and the more close you get to having that equal to zero, the more you'll have something that looks like a latency. But if you zoom in, I think it's 0.002 or 3 or something, you will see that straight out of the gate you get an output. There's no latency in this system, but you can get closer and closer to emulating it. If you zoom out to this scale here, it's gonna look like you have a delay, a pure delay in the system, but you don't. So it's all within the transfer function. Everything you need to know is in the transfer function, but you need to do those transient calculations to wrap your head around all of this. Only in the case where you do have a true pure time delay will you get complete zero down here. Otherwise, it's not. That raises another interesting issue. And that is, for a pure time delay that we saw is a flat magnitude and a straight line for phase, we need to not just look at this and not think more about it. We need to really consider that this line goes on forever, and this line, this phase, goes on forever in the sense that we have infinite bandwidth. So if you have a pure delay because you have like a transport, you're waiting for a wave to come meet you at the other end of a tube or something. Yes, you do have something. You have a delay that would be described via a transfer function like this. Or if you have a DSP delay or something, where all frequencies are delayed the same. Yes, this is how you would describe that system. But if you veer off from this in any way, you don't have a pure delay. And so you can illustrate that by thinking about a sometimes called a perfect filter. I don't know how perfect it is, but if you have a magnitude that's flat, and then it's called brick wall filter, right? So at some frequency it just rolls off. No magnitude for any frequency above a certain frequency. And it has a linear phase only to that frequency, and then it drops. Then you have a transfer function that within that bandwidth it's the same as a time delay, but outside of that or above that characteristic frequency, it has a transfer function of 0. What is the outcome of that? Well, for the pure delay, an impulse response would just be an impulse that is delayed, so this green one. You wait, and then it shoots up, and then it settles to 0 again. For this system, when you start removing frequencies, you note two things. One is that you can't realize a brick wall filter like this because the impulse response is non-causal, meaning that it would need to know that infinitely many years ago, it would need to know that at this point in time, there will be an impulse coming. So now I need to get ready to get this output. So you do see that sort of the energy is centered around the same time as the pure delay. So in that sense, it has the same delay. But you're cutting away a lot of frequencies. And so now you're seeing what's hiding behind this. And that is that in order to have that 0, that green 0, you need all of the other frequencies because they will sum together to give you that 0. So from a signal processing perspective, that's different from that pure transport delay, right? Because that would have infinite bandwidth, but if you for some reason don't, then you do have a response like that. So you could imagine instead that you don't have a brick wall, you have a more some physically realizable filter, high order. You're gonna see that it now becomes causal. So it's gonna start, you have some oscillation, you have a peak frequency, and then some oscillation afterwards. So you have pre-ringing, because the ringing doesn't come from the linear phase. The ringing comes from cutting away frequencies, but the pre part of it, the pre-ringing, comes from having linear phase. So you could make a causal system, and you'll see some of this behavior, that you have pre-ringing and some post-ringing. And so in that sense, that system will not have latency because you have an output straight away. And so again, we see that there are these different delays, at least 3 or 4, that we need to consider. The higher the bandwidth, the more closely you can follow this green pure delay. So you'll see that you have higher and higher frequency of this variation here, and lower and lower amplitude of it as you increase this frequency. But I think this illustrates the point of latency and how you really need all of these frequency components to have a pure delay. And if you do have a pure delay, the way to describe that system is like this. But if you start manipulating that system, you're not gonna have a pure delay, but you can get very close. You have that your energy is concentrated at that characteristic time that this phase gives you. Whereas for a minimum phase system, if you constructed a more realizable magnitude, that would have a minimum phase, and with that minimum phase, the energy would be concentrated more in the beginning here. It would try to, there would be a minimum lag of getting the energy out to within what the magnitude will allow it to do. But here, when we have this linear phase in this region, the energy is going to be focused around that time. So I hope that kind of clears up at least my view of delay and latency in systems. do the calculations with the transfer function and try out different situations. It's not that difficult when you get into it. So I write here transport delay, whatever you want to call it, is a pure delay. If you have a system that you can characterize in that way, you have a system with infinite bandwidth by definition. So if you start to limit that bandwidth somehow, then you're not going to have the same situation. It's not going to be a pure delay anymore. But you can approximate it. Yeah. For pure delay, all delays converge to one value. So phase delay equals group delay equals latency. The differential is 0. For all other situations, you need to do this transient response for whatever frequency that you are interested in. So do it for a low frequency, a medium frequency, and a high frequency. Look at what is the actual output, and that's how you can investigate the latency of the system. The issue with the other, the phase delay and the group delay, is that they both come from phase, and phase comes from steady state. So it's gonna tell you about steady state, and in certain situations, yes, it can tell you about the pure latency of the system, but not in general. So group delay is not in general equal to latency, but when the group delay is flat, it indicates that you have a constant slope of your phase. And if you have a constant slope of your phase, then the phase delay and the group delay coincide, at least typically. So there you would have that your group delay and your phase delay equals your latency. But latency, the way I view it, maybe there's another better name for it, that's a transient thing. When do I have something coming out of this system for a given input? Yeah. So I try to write it in one or two, one sentence here. So a pure latency exists only when the phase delay within a polarity flip, as we talked about, is exactly equal to the group delay. That's it. The system describing that delay then has infinite bandwidth by definition. In general, you should look at latency from transient calculations. Also, I said there could never be latency in a minimum phase system, because then you wouldn't be able to invert it. It does have group delay and phase delay, but also non-minimum phase systems can have phase delay and group delay, as we saw for the all-pass system, where there's no latency. The issue with inverting it is not a causal issue, it's a stability issue. And there can be apparent latency, as we saw for minimum phase systems and non-minimum phase systems. I know it's a lot to tackle, but at least that's my view on it after making this presentation. Then there's another thing that there are papers that talk about, well, how can you have negative group delay, or how can you have negative phase delay, because that would mean that you don't have causality, you have broken causality or something. When you realize that group delay is not latency in general, or phase delay is not latency either, then there's no issue with causality. There's no reason for doing those papers. Yeah, you can have a phase that goes downwards and then it goes upwards, so that now you get a slope that goes in the other direction for some frequencies. That doesn't mean that you have broken causality in any way. You have to look at latency. You have to look at the transient behavior of the system, just to discuss anything about causality in that sense. So a lot of papers, I think, could just be thrown out because they're not discussing the real issue. Yeah, here's another thing. I made a blog post recently about can you make a pure time delay via an all-pass system. And again, you can only approximate it, as we saw, but you can get closer and closer, assuming perfect components and infinite bandwidth. You can use what's called per day approximates to show that you can do all-pass systems of the bezel kind. That's at least the most efficient way of doing it, to higher and higher and higher order, keep it bezel, and then you can approximate a time delay. So if you have any interest, you can have a look at that. Then I give you a homework here, because sometimes when you have a presentation, you think, oh yeah, I get all of that. And then you get a problem, and then you think, I don't really get it after all. So I want you to look at this example and see if you agree with this old application note from Brühlink here, where they have a three-way loudspeaker system and a phase response. It says it's related phase response. That's what they show you here in solid, I assume. Try and think about this example and what we just talked about. Could this ever be the phase that you see from these three? What is the magnitude response of each of these? Is it brick wall filters? And do you then have an issue with causality? So try and fiddle with this, make some transfer functions, maybe take into account the different centers that they have. So you also have time delays on at least two of these. See what is the phase that you get and what would it take to get this phase. I haven't looked at it myself, but I think they have an issue with causality in this case here. And I think a lot of papers on phase get some things wrong about phase and delay. Maybe I got something wrong here, who knows? But let's see. At least this is my what my analysis led me to believe here. Right, last topic. We are more than 2.5 hours in. Loudspeaker phase. So this is really what we set out to look at, but I don't think you can look at it before looking into all of these other topics, because otherwise you're just discussing different things and you're not agreeing on what you're actually discussing. So let's start with polarity and phase, because we really have already tackled it, as you'll see. If you search YouTube, and that's probably not the best place to search, but if you do and look up polarity and phase, you're going to find a lot of different videos. I've looked at them all. They all get it wrong. They get different things wrong. Sometimes they get part of it right, and then something is just way off. But in general, they are not correct. I've written to some of these people, and some say, yeah, I don't really know all of those math details, so you're probably right. And others were very much insisting on they were correct. And I can show what they're doing wrong. So that's why I've done this presentation, so that we can easily tackle all of this misinformation. One issue is looking at waves and making conclusions about signal processing. I've already talked about that. Confusing polarity and delay, phase and delay, assigning phase to non-steady state situations, not really understanding this steady state versus transient. There's typically no mathematics at all. It's just feelings and very often showing some mixer program and dragging signals and saying, now I changed the phase, and no, you didn't. You changed the timing, or you changed the delay, and that gave you a phase change, but you're only looking at one frequency, so it's difficult to see what's what. So let's do it one more time here. A polarity flip is a sign flip in your system. A sign flip is described via this transfer function, e to I plus minus pi. Euler showed this, I don't know, 300 years ago, so take it up with him. The way to describe a transfer function like this is pure phase. There's no amplitude, it's just one, and it's just a flat line. It has to be pi at every frequency because there's no frequency in here. So it has to hold for all frequencies that your output is modified to minus whatever the input is. And you can calculate it via Laplace and inverse Laplace. You're gonna get this very trivial output that it's just flipped. It's sign flipped. Zero group delay, certain phase delay that is really artificial. You could flip it back and you wouldn't have this phase delay. That's why I say in some of what I write, 2 within a polarity flip, because it's going to obscure your view sometimes that you have this polarity flip. So what people often do is that they look steady state and say, I have this phase difference, I calculate what is the time delay that would give me that phase change at this particular frequency, and then I realized that, well, that can't be polarity because because it would, because at other frequencies I wouldn't have that phase that I'm looking for, or something like that. And so they argue that a polarity flip cannot be 180 degrees phase shift by looking at one frequency, and you cannot do that. You need to look at all frequencies and say everything fits. It's minus pi or pi at all frequencies. There's no latency in the system. All that's happened is that it is sign flipped. But looking steady state, yes, you can make a time delay that looks like a polarity flip, but that doesn't tell you anything. It's not a time delay. There's no time delay in a polarity flip. So a polarity flip is described via 180 degrees phase shift. So if you already have some phase change, a phase that varies with frequency in a system, and then you add a polarity flip, you can subtract or add pi to whatever phase you had before, and that will take into account your sign flip. So that's what polarity flip is. So some people have referred me to this page, and they say, well, what you say doesn't match with this page, and that seems to be a well-known page, and that's fine, but the information here is not correct, and that's of course unfortunate. We can dissect it one sentence at a time, and this is not to knock on this particular web page. I haven't really looked much into it, but there seems to be a ton of information, so I'm sure it's overall good. It's just that this view on phase is not correct. So I think it should be modified, this page. So it says in red here, there's no phase of a sine wave, and note I wouldn't call it wave because it adds to the confusion. A sine wave has no phase. A phase can only develop between two sine waves. I get it from the point of view that if you're just looking at an oscilloscope or something, and you're looking at two signals, two sine signals of the same frequency. Yeah, you can say, I don't know when they started. So I don't know what the starting phase is, but I can see a difference. But it's a little like saying I can find the speed difference between two cars, but it's not like the cars themselves have a speed. Yes, they do. The reason you can find a difference is that variable that you're looking at is intrinsically a part of each of those things that you're looking at. So for a single steady state, sometimes called non-causal, sinusoid signal, there is a phase associated with it. The phase is the phasor phase. And that's what we saw earlier, that, for example, sine omega t has a minus 90 degree positive frequency associated with it. Yes, it does require a timeline. There's some definition somewhere. But from a signal processing point of view, each sine signal has a phase. Otherwise, we wouldn't be able to do what we're doing with phase in this presentation. Next up, it says polarity reversal is no phase shift of 180 degrees, time delay, it says in parentheses. And so the thinking is that 180 degrees has to, so phase needs to be a time delay. That's really what it says here. And it doesn't. A time delay gives you a certain phase, but a phase doesn't necessarily give you any time delay. So I write here, polarity reversal is equivalent to 180 degrees phase or phase shift at all frequencies. There's no there's no pure delay associated with that. But looking at steady state only will be confusing, as there is a phase delay. There is an apparent delay when looking at a polarity flip, but there's no latency in that system. So this is not correct, and you can see how it's mixed up when you look at the presentation up until now. This one I see often also, two sawtooth oscillations. Top, the original looks like this, goes up and then slopes down. Middle, the 180 degree phase shifted signal as the period divided by 2 time shifted. Yes, it is time shifted, and this period is the period of the fundamental. That fundamental is, yes, 180 degrees phase shifted, but all of the other frequency components are not. And I say all of the other because a sawtooth like this is built up by infinitely many harmonic sinusoids. It's a periodic function, so you can do a Taylor, a Fourier series of it. And the way it's drawn, you can also see that it's not being run through a system with this time delay, because then there would be no output for a while. So this is a signal that is non-causal, and then it's been shifted in time. It's just a detail. But it's not 180 degrees at all frequencies. It's only at the fundamental. So it's not correct. The bottom one is polarity reversed inverted. Yes, it is. And that's where you have 180 degrees at all frequencies. That's what I write here. The phase shift associated with this operation is a linear phase shift. And again, you need to understand that this is not one frequency. It's infinitely many components. The typical fire button is only a polarity change, so there's absolutely no phase shifting. And that's not correct. The polarity button changes the phase of phase 180 degrees. I don't think it should be called phase button. Sometimes I've seen phase 180 button or something, which makes more sense. There's no delay associated with that. So it's not correct to say there's absolutely no phase shifting. There's absolutely no time delay, but there certainly is phase shift all across the frequency range of 180 degrees. So I hope that clears up that issue. And so thinking that phase change is equivalent to a pure time delay is an issue. Not realizing this thing with, unless you're looking at a pure sine signal, there are many frequency components in your typical signal. Even when it's periodic, if it's not periodic, then you have continuously many frequency components, infinitely many of them. And then looking at steady state and making conclusions that you can only reach by looking at transient behavior. And the remedy here is to understand phase delay, group delay, what I've talked about, latency here, and how to calculate the transient response via inverse Laplace analysis. This thing with frequency components, that's Fourier series and Fourier transform analysis. And this steady state versus transient behavior, it's again Fourier and Laplace and the inverses of those that are needed to understand those aspects. Since this comes up in many blog posts, there's always confusion about it. I made a single slide that explains all of this in one go, and I posted it on Audio Science Review. And in the beginning, people came into two camps. One camp says, this is trivial, why are you even showing it? We know this. Another camp said the usual, no, it's not 180 degrees because that would entail a time delay, and there's no time delay. And I show how you can get confused if you just look at a single frequency. You cannot see properly what's delay and what's phase change if you just have a single frequency. They're going to look completely the same, but you have completely different impulse response, for example, and overall behavior is different. So you can search Audio Science Review, and I think you can download this. Yeah. Okay, crossover phase. I looked at crossovers back when I studied many years ago, and I was super interested in it. I don't know why. I think Klaus, my old professor, he was very good at making it interesting somehow. So kudos to you, Klaus. And I read a lot of older AES papers at the time, and I could see the nomenclature at that time was grouping into constant voltage types and all pass types. So this constant voltage type is what I said earlier. It's just a transfer function of one. Whatever you send in, you get out. And that's transient perfect. So anything you send in is going to come out perfectly. You could have -1 here also if you allow for a polarity flip. Sure, you can do that. And it's a special case of linear phase. So any linear phase system with flat magnitude response is going to be transient perfect, but this is a special case of transfer function equal to 1. And then there's the all pass types where the magnitude is 1, and then you have some phase. It's not transient perfect except for the DSP linear phase type. So we will look at that a little later on. And so what is this transfer function? This transfer function is the total transfer function for the crossover. So if you have a two-way crossover, you would have a high pass section and a low pass section. Those two combined, what is the total transfer function of those? And the ideal is some kind of all pass type. You don't want humps or dips around the crossover frequency. You want something that's flat. and maybe you are not too concerned about the overall total phase. And that's what's being said a lot, and why the total phase is often not even shown in measurements, because it's said that we can't hear that. All we hear is the magnitude response. And I would, I'm not in total agreement with that, but we can look at that later. So this transfer function here is the total transfer function. So let's try and look at the ideal, the old way that years and years ago, certain loudspeaker companies tried to obtain transient perfect loudspeakers by using first order filters. In this setup here, where you have an overall transfer function that equals 1, and you split that into a low pass and a high pass section. You of course have your drive units too, right? Your tweeter and your mid woofer. So either you need a very big overlap between the two, or that they somehow roll off themselves as first order. I imagine it's very difficult to obtain this, but at least a lot of work has been put into it years ago. So this will be transient perfect. It will sum up to 1. So whatever you input will be output the same way. It has a completely flat total response. It rolls off with first order slopes. It's not what's called phase coherent, so the high pass part or section doesn't have the same phase as the low pass section, but they do have the same characteristics. They have the same slope along the way, and the sum is 0, as it has to be, because the total sum is 1. I didn't show the radiation characteristics or the beaming polar radiation, but that will probably have some issues since the phase of each of these is not the same. Then it's often said that what we just saw, this first order crossover, is the only way to get this precious constant voltage type that equals 1. That's not true. I can see why that would be the thought, but that's not true. You can make a 3-way filter that also sums up to 1. So like this second order 3-way filter. So you start out with this all pass or constant voltage transfer function, second order polynomial in the numerator, and also second order the same polynomial in the denominator, and then you split it out to a low pass, a mid, and a high pass, and you can even vary the Q of these sections, and they will sum up to 1. So that shows us that there's another way, probably infinitely many ways, to obtain this constant voltage, but you need to go up in multi-way, not 2-way. So in this case it's 3-way. You need to choose a certain Q to plot. So here I plotted for Q equal to 0.3. And they sum completely flat. Second order slopes here on the high and the low. First order slopes on the mid section here. Not phase coherent, but the sum of the phases is 0. So at least there's that. So this has actually been investigated, I think in the 70s by Bang & Olufsen. There's a paper on it. I think they had limited themselves to a particular Q value. I don't really know why, but in the paper I think it's square root 2 or something. There's no need for that limit on the Q as far as I can see. But it never really gained traction. So while it should be better when it comes to overlap of drivers and things like that than the two-way filter, it just never really got anywhere. Right, so let's now move into the all-pass type, where we let the phase go in some sense. We are only interested in the sum being flat, the magnitude sum being flat. In this case, I have s minus 1 in the numerator here. I could have minus s plus 1. That would mean a polarity flip overall, but I've chosen it this way, so yeah, so the high pass sort of has the correct leading edge, as we talked about earlier. Right, so this is not gonna sum to 1, but it will sum to a flat magnitude response. And then you have a certain total phase coming out of that. So this is our all-pass phase. We can see at low frequencies that phase is completely dictated by the low frequency section, because that section now has a lot larger magnitude than the high pass, and whatever has the much larger magnitude will dictate the phase, because the smaller one is just a little phaser in comparison. And you see at high frequencies the total phase is dictated by what the phase is for the high pass filter. Yeah, it's not phase coherent, but and if you're gonna make this somehow, you might just, why would you go for this minus? Take the plus and get this transient perfect. But anyway, I show it here as an example. It's probably difficult to realize either of them. Here I say what I already said. When you plot this phase delay, I had to do some phase wrapping and adding pi and things like that. It's not necessarily that easy to plot. Yeah, I think I also corrected for polarity flip. So there is this sense of a polarity flip it's kind of polluting the overview of your system. So it's not that polarity flip changes the overall characteristics of the system when it comes to latency and things. It's just that to make your analysis easier, you typically have to consider flipping the polarity, doing your analysis, and then flip it back in some sense. Again, because the phase delay is gonna be affected. The group delay is not, because the slope is gonna stay the same. Here is the second order three-way all-pass system that you could consider making if you want to. Very similar to what we've seen before. You would just have a certain total phase, a flat magnitude response. But again, why make this one if you could make the plus version? So instead, I move on to Lindquist-Riley. So these different filter types, Lindquist-Riley, Butterworth, they're often presented already in this split state where it's low and high frequency sections. or low pass and high pass. I think it's a bit of a shame that people don't also plot where did it actually come from. So in this case, the way to think about it is that you could have an all-pass first-order filter section multiplied by a first-order constant voltage section. Multiply them out, and this is what you get. And you have a Q value on the second-order parts of 0.5, and that's what the Lindquist-Riley characteristics is. That's a Q of 0.5. But you miss the essence if you don't write it like this. You miss the essence that it's actually in total a first order all pass system, because this constant voltage system is not going to change anything. It's just one, and we already looked at how this behaves, so we already have some idea as to what this should sum up to. But the fact that it sums up to something doesn't mean that there aren't different ways to get that sum. And so for the Lindquist-Riley, yes, you get a flat response, but you have second order slopes now instead of first order slopes. And I think that's interesting to note, that there are different ways that you can get to the same total transfer function. And here you have the same total phase as we saw earlier for this system, but now the low and high sections have phase that also coincide with this total phase. So now it's phase coherent in that they are all the same. They all have the same phase. And that's an advantage when it comes to the polar pattern, having this phase coherency. Otherwise, you might have correct flat on-axis pressure, but if you lift your head up a little bit, it changes a lot, and if you sit too low, it changes. This one has sort of guaranteed symmetry in your polar output. So that's a nice feature of this. There's one thing that we'll look at a little later, and that's this, I don't know what it's called, I call it null test in this case here. What happens if you flip the polarity of one of the sections? So you invert the sign of one of these. In this case, for this filter, you get a deep null if you flip the polarity of one of the sections. As we'll see later, that is not a general thing. You cannot necessarily evaluate a filter on how deep this goes, but let's wait a little bit with that. There's a certain group delay, a phase delay, but we have seen that because this is for the total output, and we already have plotted it for this first order all pass. So no surprises there. There's yet another way to get this total first order all pass section, and that is to multiply it with a particular constant voltage transfer function like this. You have a very particular value of 1 here in front of the S, and multiply all of that out, and you get what's called a Butterworth, a third order Butterworth filter, and we can check the coefficients to see it's 1, 2, 2, 1, 1, 2, 2, 1. So this is Butterworth, a Q of 0.7, but the overall characteristics is still a first order all pass filter, which is never really mentioned. So yet another way to get the the total, the flat magnitude response, but now you have third order slopes for the low pass and for the high pass sections. The scale is a little different now. So you have the same total phase as before, but now going to higher order filters, each section has more elaborate phase than we have seen before. But the total sum, so the on-axis, is still, the on-axis response is still the same as for Lindquist-Riley, but the polar pattern will be different. So the radiation will be different. And these are not phase coherent. So that could be problematic. But in another sense, it's higher order slopes, and that might be just what you're looking for. I think this is the the polar radiation. So on axis here we have a certain value, which is the value magnitude that we will have at all frequencies. Lift your head up a little bit, you get something not so high in value. So you could sit up here and you have a dip around your crossover frequency. So that could be problematic. Then I thought, what about putting a minus sign on this part here? And again, I'm just fiddling really with this, and I see that I still get 1, 2, 2, 1 in the for the poles here. So this has to be a Butterworth filter still. But now I don't have a minus sign here, I have a plus. So that's interesting, and I had to look up if this was well known. I didn't know. I did find some blog post that says, yeah, there are 2 versions of Butterworth, and one has more phase change over frequency than another one. So it's well known, it's just that I hadn't looked at it. So this is interesting because in total it's going to behave differently than from what we just saw. So it's still third order. Third order slopes. It still has a flat total magnitude, but now the phase is different. So there's, for the total, there's more phase variation in this frequency range, which is to be expected because you have a higher order all pass filter than you did for the other version. And you can compare the group delay for the first version to the other one, and the first version is more flat. It's gonna depend on I guess the Q is fixed. So yeah, it's you're gonna have a peak in your group delay for the alternative version that we just looked at. So they are not the same because the total is not the same. As far as I could see, it has a flipped polar radiation pattern, which I don't even know if that's a problem. If it is, then you could have the tweeter below the mid or something. But it illustrates that you shouldn't let's start with the last one here. You shouldn't dismiss a filter based on one section having a minus sign. So if you open up a loudspeaker and you see, I see the red wire goes to minus on the driver, something must be wrong. No, you have to trust the designer that hopefully had some idea as to which transfer function he or she was trying to get at. Because you can see that the first version with a minus sign actually has better performance in some sense when it comes to group delay and how much phase distortion it's gonna have. Whereas the other one, where it was plus and plus, added up to a second order all pass, which gonna have more phase change and more phase delay. So you shouldn't just look into a loudspeaker and say, oh, this has to be wrong because I can see something is flipped here. Maybe it is wrong, but I would hope that it doesn't get better if you flip it. At least that shouldn't be your first thought. If you're opening up and flipping things around, you might as well redesign the entire filter if you're interested in that. And so you could investigate transient response, see which one has the best transient response. And in this case, the first version with the minus sign on one of the sections would have better transient response, if that's important to you. And another thing is that for those filter types, you cannot do this null test because we just saw two versions where one had a flip polarity on one of the drivers and they both sum flat. So if you have a complex number, two complex numbers, and they are 90 degrees out of phase, for example, and then you flip the polarity of one of them, then you're turning the phasor of that one phasor section. You're turning that phasor 180 degrees. So now they're just minus 90 degrees out of phase. So they're gonna add up to the same magnitude. It's just at a different angle. So for certain types of filters, yes, you can do this null test. For others, you cannot. And if you think about how a loudspeaker designer designs a crossover, I don't think that it is, at least always, from what I've seen, it's not sitting down and writing equations and transfer functions. It's fiddling around with components until you get something that's reasonably flat. So it probably isn't a Butterworth or a Lindquist Riley. It's something in between. Maybe you don't even have the same characteristic frequency for your high pass and your low pass. It's just, it looks fairly flat and the phasors are what they are. So you shouldn't expect this null in general. You could have a bump or a peak or something if you start fiddling with flipping polarities of drivers. And I know that's strange if you think in terms of real numbers, because when you have a plus, you're summing numbers, so that has to be bigger than if you take a minus sign on one of them. Then now you're subtracting numbers. That has to be smaller, right? You can't think like that when it's complex numbers. And so this is the main issue I see with engineers, that they don't carry the theory that they learn when studying with them into engineering. Then it becomes more trial and error and fiddling and things like that, and it's gonna lead to issues. I've seen it so many times, but that's a topic for another video, I think. You can go even more complex. So Sten Duelund, a Danish now late loudspeaker designer, he came up with some transfer functions also, and they are also phase coherent, high order, and multi-way, so three-way and four-way. So again, it comes down to multiplying all pass and constant voltage type filters and seeing what you get. So in this case, he got fourth order filter sections in a three-way configuration like this. I did plot them, yes. You have a Q that you can vary. Yeah, and I think for some Q values you will have that it's actually subtraction, so you have overshoot on the sections, I think, but I haven't checked. So here it just shows a Q value where I'm sure that it's a sum that makes the total. So we have high order slopes, which could be good. And then you have this phase coherency again, that all of the filter types are, or all of the sections are in phase with the total phase. So again, it should be good for the radiation pattern. Sorry. Yeah. So the late Sten Duelund has a web page where you can see more about this filter. And actually my own first journal paper was written about these filters from Duelund and how to implement them with active filters in a clever way with equal valued resistors and equal valued capacitors. So they have a little bit of a special meaning for me. One thing to note is that for a Q value of 0.7, this converges to a fourth order Lindquist-Riley. Again, that is phase coherent, and we have plotted it here. So imagine that the bandpass or mid section for Q's closer and closer to 0.7 just tends to go away. And right here at 0.7, all that is left is the low pass and the high pass section. And so that's what you get. You get Lindquist-Riley. You have minus 60 dB at the crossover, like you should have. And you have this phase coherent phase for all sections and the total. And you can take it even further, and he did. So you can try and multiply this out where you have two all-pass sections and two all constant voltage sections here. You get a sixth order four-way filter. But again, it's important to realize what is the total and where did that total come from. Yeah, I didn't multiply it out. I didn't show anything about it. One thing I want to show is if you take this all-pass section here, that is what you had for the Lindquist-Riley second order and for the third order Butterworth. They amounted to the same thing in total. If you look at the step response, I am wondering where the blue curve is. All right, it's just that they're of course going to have the same step response. So the blue one is hiding behind the green one. So we have a step response for this filter type, which could be Lindquist-Riley or Butterworth in one of the configurations at least, where it goes up, follows the step, and then it goes down to -1. If you look at the high pass section and the low pass section, just for this all pass filter, you can see that it's the high pass section that makes sure you get up here at the leading edge, and then it dies out to 0, whereas the low pass section also reacts immediately, but you could say more slowly, and then that is what carries through the behavior at later times. And then we have the second order all pass section, so that could be fourth order Lindquist-Riley, and also the Butterworth, the alternative third order Butterworth. And here you get a step response. Again, it goes up, positive leading edge, you could say, but then it can't follow the step. It goes down, and then it comes up again. It fits with what we see at high frequencies, what we see at low frequencies. At mid frequencies we have this minus sign. They don't have exactly the same Q, so you're going to have some differences here in the temporal response. But one thing I mentioned here is, what about polarity? Which polarity is correct in some sense? Well, I think it's easier to see for this section that this is probably what you would say is correct polarity, if you have to say anything, that you have the leading edge here, you're coming up following the step, but again you can't really, so it goes down. And at lower frequencies, yeah, you're going to have the correct polarity in some sense. I think it's more dodgy for this version here, where you sort of have to choose, yeah, am I going up and following the step and then having the opposite output signal of what I have as the input, or what? So I think polarity is, it's often discussed on its own, but you need to discuss it with whatever phase that you have already to determine what is the correct polarity in some sense. Because all it can give you is this pi or no pi, I was going to say. So 0 or pi added, which do you prefer? It's not always that clear. There are of course many papers on other types, like asymmetric crossovers, where you don't have the same slopes for the high and the low and all of that. John Kreskowski has a good page that I remember reading a lot back in the day. I think it still exists. Many types, and this is just looking at analog filters, so not even getting into DSP. A lot of things to study there. Then also we need to consider that we actually do have drivers, right? So I think the easiest way to do it is just to consider an active implementation of the filters. So you have like operational amplifiers. So you can split the filters or the transfer functions. So you could have a high pass crossover, some amplification, and then a transfer function for your tweeter. And we'll talk about what that is. But you have the same for the low frequency, and you have a woofer that has a certain transfer function, in some sense, at least. And then your output is going to be the sum of these two systems multiplied and these two systems multiplied. But now we need to consider again that the signals and then the fields, and here we're threading into the field aspect in that, yes, you can have a lumped circuit that describes your driver, but really it's a 3D thing. There's a displacement field sorry, on the cone and surround. You might have modes. We talked about phase decomposition in an earlier video. It becomes a little bit squirrely to talk about a transfer function in some sense, because when you go out to the pressure point that you're looking at, so the microphone point, where you're interested in what is the pressure output I get for a given voltage input somewhere out here. You're essentially looking at a phase of that pressure which comes from many small surfaces on the woofer and tweeter, and they're not necessarily moving in sync all over the surface. And so you could measure things like, oh, my drive unit is not minimum phase or something, but I have a transfer function that's minimum phase, so what's going on there? Well, it's just that when you move into this field aspect, it becomes more complicated to even define a transfer function. So we often do it right. We just measure something. There's a pressure magnitude, pressure phase. I know what my input voltage was, so I can find a transfer function. Yeah, you can, but you need to not be too conclusive about what you measure. Like this, is it minimum phase or is it not? You need to be careful about those types of conclusion. But at least we see that the output when it comes to the pressure is something that is summed, and that's important. And we'll get to that. For a passive implementation, it's a little more difficult for me to write because the drive units themselves would load the passive filter. So now it would be just one big transfer function for that setup. But again, you would be summing, you would be within this field aspect of things, and you need to consider that. Yeah, there's a thing about looking at a total transfer function, which has some magnitude and some phase, where it can be a very good idea to split it into a minimum phase system and an all-pass system, and you can always do that. So you have a certain magnitude that is the same as for the total. Then there's the associated minimum phase to that magnitude, and then whatever else you have of phase goes into this all-pass system that just has a magnitude of 1, so 0 dB, right? And then it has some excess phase kept in here. So if this total transfer function really is minimum phase, then this is just one phase 0. There's no excess phase. But if you do have excess phase, it could be from your measurement where you have like a meter distance to your, let's say, to your baffle, because again, what is your distance really to a loudspeaker driver? It varies across the surface, right? That's why I say you need to be a little careful when it comes to fields. But let's say at lower frequencies that there's a very distinct distance of 1 meter. You could put that into the all-pass excess phase, that phase that comes from that time delay or that propagation. You could put in here. It's not really of interest to anyone, so you don't typically want to see it in a phase plot. And that's an interesting aspect of measuring a loudspeaker, because the magnitude response is found in 1 meter, for example, but the phase response is recalculated to where it sits on the driver in some sense, because you don't want that added phase coming from the distance, right? But you also can't measure an appropriate pressure right near the driver. That's going to give you an incorrect magnitude. So you measure at a point, and then you subtract the phase that came from the propagation to get the more proper phase of the system, right? So you could put that delay in here and then just investigate the minimum phase system if it is minimum phase. Otherwise, this all-pass system would have some phase coming from a delay and then some more phase coming from this system, not being minimum phase in general, even without this transport delay. But from what we have seen now in this presentation, I would actually suggest refining this a little bit and say, yes, we have a total system. So that could be the complete pressure or the complete system of a total loudspeaker with multiple drivers. And here you have a transfer function describing what is the pressure, the complex pressure that I get for a complex voltage input. That is what my system describes. And then I would suggest this 4 section setup, where you make one section take into account polarity, because we've seen that can pollute phase delay, for example. It just muddies the water somehow. So you could have a system that takes into account polarity flip if you want to. And then you have a minimum phase related to that whatever magnitude your pressure, for example, has in your measurement point. And then you could split your all pass into 2 sections. One that takes into account the non-minimum phase aspects of, for example, having right-hand side poles, zeros. So it's not that there's any latency. It's whatever. The issue with this one, when it comes to inversion, would be stability, and then have another one for a pure delay, where the inversion issue would be with causality, right? So if you know you have a distance of 1 meter, you could put that into this one, and then if you truly have a minimum phase driver, if you're measuring a driver, this one would not have anything. It would just be 1. You would have your driver characteristics here, and then you would potentially have a polarity flip. I think this is a good way to split the terms even further. Okay, so I already mentioned it. Are loudspeakers minimum phase? If you look at the transfer function for a single driver, it's typically like a high second order high pass and maybe some first order roll off at higher frequencies. It's in essence a minimum phase transfer function that you have for that driver. That does not mean that the total loudspeaker, the complete loudspeaker, is minimum phase, and I want to illustrate that. So how do we do that? The best way I could think of was just to imagine the a magnitude response for a loudspeaker. And that's what I have here. So I don't have anything on the axis here, but it's frequency and then magnitude up here in dB. Where what you probably are hoping for, at least, is some flat pass band and then some roll off. I have second order on both ends here. It doesn't really matter much, but a wide bandwidth where it's just flat amplitude. And so if it's infinitely wide bandwidth, we have a flat response at all frequencies, and the minimum phase associated with that is just 0, because that would be the magnitude response of a wire, and that has to be a 0 phase. The minimum phase has to be a 0. And so we limit ourselves here. We band limit ourselves. So we say we do have slopes, we do have some roll off at either end. But what is then the minimum phase that this system would have? Ignoring variations, of course, you have dips and peaks and things that are difficult to put into a simple system like this. But for now, you could imagine that whatever variations you have tried to parametrically EQ your way out of. So imagine you have a very good speaker, it's very flat response. What is the phase that you would expect if that were a minimum phase system? Okay, there are some guidelines that Bode gave us for figuring that out. There are some rules for how you draw the phase for a system like this. As an EE engineer, you learn how to do that, so hopefully you can remember that. So I did that, and so the asymptotes should look like this. So you should have a phase that starts at 180 and varies gradually towards the zero. I was talking about the zero phase that has to be somewhere in the middle here at least, and then goes into another slope here, and it flattens out at minus 180 degrees. This is the asymptotes for the minimum phase of a magnitude like this. So a prototypical made-up loudspeaker would look like this. And I thought about ending it there and just saying, this is not what you measure. So a total loudspeaker is not minimum phase. But that wasn't quite satisfactory enough, I could imagine. So I made the transfer function. So in this case, it's a very wide bandpass filter, and I made it as a low pass section and a high pass section, and you can do that if the characteristic frequencies are very wide apart. So I have these two sections that I then multiply, and I have the red asterisks here is my total response. So I have made a filter that has the amplitude response and magnitude response that I was looking for. I know there are no extra poles and zeros, so there's no excess phase that I have artificially put in there. This is the simplest way I can achieve this magnitude response. Knowing the magnitude response, I can plot everything I need. I can plot the phase of this system. And we can see that it follows my asymptotes, but it's much more smooth. It goes from 180 degrees, it varies, it goes towards zero, so it's fairly flat phase here in the passband, and then it rolls off again, and it goes to minus 180 degrees. So my asymptotes were correct. You could draw this slope or this phase from those asymptotes. This is the minimum phase for this magnitude response. And so what you would need to look at is measurements. If you have a loudspeaker that measures very well and is very flat, you need to look at the phase response and compare it to this. If it doesn't look like this, then your system cannot be minimum phase, because then it would have this phase. So and this system would have very nice temporal behavior too. So here I put in a step response. I hope I did it correctly. I think I did. It makes sense at least that the step response cannot shoot directly straight up. It has some slope here because it doesn't have all of the high frequencies needed to go straight up. But it's very smooth, a little insignificant bump here, and then it rolls off because it doesn't have DC, so it has to roll off at some rate. But very nice response. And so again, you could ask yourself, is this what you measure when you measure a loudspeaker? Probably not, meaning if it's a very flat response and it has a very unsavory step response, that system cannot be minimum phase. It has to be non-minimum if it doesn't look like this and it has approximately flat response like this. And so one way to show the issue that you have is that you sum things up. You have a crossover, you have multiple drivers. So I emulated that, or I modeled that, you could say. So I took a second order Linquist-Riley, which is a fairly benign filter. I think it behaves fairly well. And I expanded my two sections. So now I have a section for my low frequencies and a section for my higher frequencies. They meet here at minus 6 dB, as they should for Linquist Riley. Some flat across the board here, and I essentially have the same magnitude response as I did before. So again, you could imagine I'm measuring this. I have a two-way speaker. It's been realized somehow with a second order Linquist Riley. Great drive units that have great overlap somehow. And everything is dictated by the crossover. Do you get the same phase as you did before? No, you don't. You get this phase. Showing you that this is not minimum phase. It cannot be minimum phase because we already saw what the minimum phase was for this magnitude response. And so you can also calculate the step response for this, and I think we already looked at it for this essentially first order all pass section, that it goes up and then it goes down again to -1, and then it goes up again because again we're missing frequency components. But I think I did this correctly. It was a lengthy calculation, but it made sense. So if it deviates from the minimum phase step response, then it cannot be minimum phase, because then it would have the same step response for the same magnitude. And the issue is essentially that most loudspeakers have summed outputs. So you have something coming from one driver and something else coming from another driver, and they have some overlap, but the total output is a sum of some transfer functions. And this is just what is very essential to understand, that if you have minimum phase systems that are cascaded like this, the strategy of just plopping the poles and zeros on top of each other work. If you don't have any right-hand side zeros in either of those, then there are no zeros to put there. So it will be minimum phase if these sections are minimum phase. And so that could be the crossover combined with one of the drivers. That could very well be a minimum phase system looking isolated at that. But if you have a system here, and that's minimum phase, and that could be these two multiplied. So it's the crossover section, let's say the low pass, and or let's say a high pass and the tweeter here, and this transfer function is the low pass and the mid woofer, and they are perhaps both minimum phase. When you start summing minimum phase systems, there is no guarantee that you will end up with a minimum phase system. Most likely you will have a non-minimum phase system, and that comes from how complex numbers work. That it's when you add and subtract, you need a different strategy than when you multiply and divide complex numbers. And so it's not easy to see why this is, but we could have shown it, or we have seen it for the transfer functions, for the crossovers that we've looked at, that they have a flat magnitude response and some phase, and therefore they are not minimum phase. They are by definition non-minimum phase systems, because they are all pass systems and they have some phase. And were they minimum phase systems, they would have zero phase because they have flat magnitude response. So your typical loudspeaker cannot be minimum phase, but you'll often see that in blog posts and things like that. And I think people are confused by the drivers themselves perhaps being minimum phase. The system as a whole is probably not. But you'll have to just look at your measurement system might be able to tell you what is the excess phase. If there's any excess phase and it doesn't come from the distance, if that is taken out and there still is excess phase, then you don't have a minimum phase system by definition. And also if your step response is all over the place, it goes up and down and up and down, and you still have a very flat magnitude response, that also indicates that you don't have the minimum phase step response, because it should look much more smooth and transient perfect. If you have a very wide frequency bandwidth and very flat magnitude response, you should have a very nice step response. You should have very nice temporal behavior, transient behavior overall. So if you don't have that, then that indicates that you don't have a minimum phase system. As I've said here, transient response gives insight. You can look at how much a step response varies from the ideal. And of course, if you have some way of viewing excess phase, it tells you what you need to know. It could be nice if it could also maybe calculate what the step response would be for the minimum phase part, but I guess that's a little much to ask. Right. Okay. So we're closing in on 4 hours here. It's all in one go, no manuscript. So yeah, we're almost there. The last thing I want to talk about is absolute polarity. That really is about, is the overall sign important? So imagine that you flip your wires on your loudspeakers, both of them. So all you've done is change the sign of the total output. So whatever pressure you measured before, you'll get the same magnitude, but the phase is 180 degrees shifted up or down or whatever. So the sign has been changed in the overall output. So you're not flipping the polarity of one of the speakers, because then it's gonna really mess up the sound. So somewhere you're flipping the polarity of both your speakers. I'm assuming a stereo output here. We already know that operation, that system that describes that, is a polarity transfer function, e to I pi or minus pi. We plot the magnitude and phase. So this is what's happening on both left and right. And I've seen some lists of correct absolute polarity where I think people have scanned vinyl records or something, looked at, somehow figured out what is correct polarity for records, for certain record labels or something like that, which it doesn't really make sense to me, but we'll talk more about that. There's also what's called the Wood effect that I've never really looked into, but now I've sort of had to, where for certain test tones, like this clipped sine here, where so you clip the top of a sine. When you flip it, or polarity flip it, now it's the bottom part here that's been clipped. Apparently there should be an audible difference between the two, and I've only just recently listened to this. I'll get to that. So something about absolute polarity is being discussed, but I think people are forgetting the overall loudspeaker phase, right? Because you can only do so much with a polarity flip. If your loudspeaker in itself has a lot of phase distortion, then I think it's difficult to talk about absolute polarity, because at what frequency do you want it to be inverted, or what is your goal? We saw that for step response, it can be difficult to say really what is my goal. Do I want that leading edge, or do I want the later response to look like my input? So I think it's a bit strange to talk about absolute polarity as something absolute, because I think people should be in disagreement even within a record, or between tracks. They should be in disagreement, because if that track has a lot of focus on one type of instruments, and the next track has more focus on some other instruments that play at a different frequency, and you have your loudspeakers, and then you compare to a person who has some different loudspeakers, you might be in agreement about phase for certain instruments, but not for others. And certain instruments will have their harmonics distorted because of the phase change. So I think it's tricky to talk about absolute polarity in some sense. I got this from Erin, and I think there's something wrong with this phase, because it goes upwards. I think there's too much delay removed or something. But in general, this was just to show that it's not like a loudspeaker has 0 phase, and now you come in and flip polarity, and now it's 180. No, you shift whatever you have, whatever strange phase that you have, you shift that 180 degrees up or down. There's no correct phase or correct polarity, I would say, and I would imagine that there would be disagreement if we were super sensitive to it. I don't see how there could be agreement across all loudspeaker as to what absolute polarity is. So one thing to realize is, again, you can have different step responses from different loudspeakers, for example, meaning that your music signal for different loudspeakers will also look differently if you recorded it, and a lot of that is coming from the phase. So if you have very flat magnitude, you have 2 different speakers, they measure well magnitude wise, but they have very different phases, your temporal behavior is going to be different. So I think it's strange that loudspeaker phase is neglected. It's said like our ears are not sensitive, so let's not look at that, because here's something where at least you would measure in a null test, you would measure a difference between 2 loudspeakers that had the same magnitude response but different phase, because they would distort. There would be temporal distortion that would be different between the 2. And I think with DSP and new speakers coming out, it's much easier to test, because, for example, for these key 3s, you can see there's a low latency mode, which corresponds to some minimum phase filters, you could say. Not that the entire thing is minimum phase, as we talked about, but I think this is a very, on the right here, a very typical step response from a loudspeaker. It goes up, it wobbles a little bit, and then it does something. And this is where a lot of people say, well, it doesn't matter how it looks here, as long as the magnitude response is flat, then all that's all we need to look at. But these speakers, along with a few others, they have a setting where it goes into a linear phase mode. So you essentially get that minimum phase that you were looking for, but not 0, not completely to a 0 in the passband, but to a linear phase. So you accept that there's a time delay, and you can see that there's a lot more latency in the step response. Here it says 92, and here it says 5. So that's the downside of this DSP. But you can get a much improved step response in this case, where you linearize the phase with DSP. And so now you have a comparison that you can do, because you have that flip, that switch, so you can just try it and see if it's really true that it doesn't matter, that all that matters is magnitude. Now, I have visited Purify some time ago, and Bruno Pozzi was there, and he had these, and I listened to them, and I wanted to hear this, if there's any effect. So Bruno asked me, what track do you want to listen to, and I didn't know which track would reveal anything. So he chose the track, and he didn't say anything. I've never heard it before, but he just started it. I listened, and I could hear him clicking back and forth like every 20 seconds or something like that, but I didn't know which position it was in. And for a long time I was thinking, this is embarrassing. I don't know how to tell him that I can't hear a difference. There was I didn't really hear the music. I was just thinking, what am I gonna say? I don't want to offend anyone. So I thought, okay, I'll give it the good old college try, or whatever the saying is. Now I'm gonna focus. So I was like a minute in, and I tried to listen to anything with timing. So I wouldn't consider myself an experienced music listener. I'm more on the mathematics side, but I knew that it had to do with phase, so I understood the signal processing of it. So I knew I had to look for something with timing. And I don't know if he chose that track in particular because he knew there was something there, but there was an instance, like very brief in the track, where a lot of instruments had to sort of start or stop at the same time. And in one setting, it was like ding, ding, ding. I heard those different instruments at different times, and I thought, oh, I think I'm onto something. So I waited for him to flip into the other setting, and before he flipped again, that same portion of the track came, and now it was just boom. Everything was sort of in line, but for the rest of the track, I couldn't hear any difference at all. So in my blind test, but knowing what was being flipped between, I could figure out which, not just the difference, but I could figure out which was which. So I turned around and said, it's linear phase now, and he just laughed and said yes. So there is something there, but how important is it? I don't know. I hope I can talk to him and get that track, because it was really interesting. Because based on the papers I'd read, I would say no, it doesn't matter. Phase doesn't matter at all. And I changed my mind that day, because I was not prepped or primed anything. I was just trying to listen for any difference. So that was interesting. Then I tried this polarity check. Now we're back to polarity. The other thing here I think makes a lot of sense, that perhaps for certain tracks, certain test signals, you can hear this temporal difference between linear phase and more standard phase. I also listened to this one where it's absolute polarity. So a track is being played, and then it's flipped in polarity, and then you listen. And I wish I could get the tracks, because now you have to click here and stop this one, and then start this one, and so there's a little bit of a lag. So here I couldn't really hear any difference between the two. So I thought, okay, I guess polarity is not that important. But then, Then I thought, oh, I've never listened to this wood effect. I've heard about it. I better listen to these tracks. So there's a blog post that describes the signals, and also you can download the signals and a little player where you could set it up and listen in a good way to these. I thought, okay, now I'm not gonna hear any difference. Let's get it over with. So I played it. It plays the first track, and then it goes directly into the other track. And gotta say there is a difference, at least to my ears. It's like a slight pitch change. I would say if there's any pause between the signals, I think it's very difficult to hear. But if one goes straight into the other, then for me there is a difference. I asked a friend of mine, he could also hear a difference. I should say I listened with headphones, and I didn't try loudspeakers. It could be that it's more difficult there. But my friend could also hear a difference, but for him it was more like a perception of loudness difference. But I didn't do any more with it, because I've spent so much time on this presentation. But I see the issues that people have when they discuss things like cables and DACs and all of that, because you enter an area where, as I write here, you could easily make a journal paper, peer-reviewed, everything, that shows that polarity flip or absolute polarity is not important at all, and in the same paper that the general phase of the loudspeaker is also not important. You could easily show that with the right signals and the right music. And on the other hand, you could make a paper where you hand select signals and small pieces of music, like the one I listened to, and you could, I think, easily show that there is an effect of both polarity and general overall phase of a loudspeaker. And I get it. I get that it's a tricky thing, and people get very emotional about what they can hear and what they can't hear. I think it's a bit of wasted energy, because if you like a cable, if you feel like you can hear a difference from a cable, then who am I to say that? Well, when I do the modeling, I don't consider anything with cables. It's just a transfer function of one. So what are you talking about? I think it's not really even worth discussing much when it comes to cables and DACs and these things, where people go into these camps of there's absolutely no effect, and in the other end, I hear a big difference between cable A and cable B. I think that's in this fringe area where you should just trust yourself and say, okay, I like this cable, I also like how it looks, and it has a good grip on my terminals. There's no need for me to discuss this on any forum. And certainly for someone like me who's very much into the mathematics, it doesn't make sense for me to comment on cables or something like that, because there isn't anything that I can model. I can't really, well, we could do some transmission line modeling. I could show the field from a wire, or something like, is there a field when a wire is just plugged into the wall socket and just hanging in the air? You could illustrate those things, but I think it's a bit of waste of energy to really be super passionate about those subjective data. Certain people can hear certain things. If you get experienced and sensitivized, you can get better at hearing things, and maybe now you get really annoyed about something you didn't get annoyed about before. So is the overall sign important? Yeah, I think it is a little bit important. I think the overall phase of the loudspeaker is gonna affect this, so you can. It's difficult to separate the two unless you have some DSP, so that you can try these different combinations. But I think I've said enough. Okay, so some takeaways. I had a lot of them in the presentation. Here I just want to say, don't try and look at special cases and infer generality from that. That's what I see a lot. People look at very specific frequency and steady state, and they make assumptions about how a delay and polarity flip relate to each other, and they're looking at a special case and they try to make something general out of that. That rarely works. So this thing about steady state tells me everything I need to know. No, it doesn't. You need to look at transient behavior too, because otherwise you don't know where it came from, what the system was that made this steady state behavior. This phase is just a time delay. You need to let that go and say, yeah, time delay can be described via a linear phase, but that's it. Don't judge a crossover by its sign, meaning that if you see something that hints towards a polarity flip of your tweeter or whatever, you gotta trust whoever made this. Of course, if you're curious, you can try and change it. But we just saw that the version with the sign, the apparent sign change, could be the better version. So maybe don't try and change that. The null test for crossovers, it's not a fundamental thing. It's not a way to test how good is my crossover. It depends on the complex phasors that you have in that region. Then am I looking at a signal? Am I looking at a system? Am I looking at a field, or is it a combination? And signals are not waves in general. What else? We went through this minimum phase versus non-minimum phase. I would say that most loudspeakers are probably not minimum phase. The drivers probably are from a signal processing perspective, but maybe when you measure it, you don't quite see that at higher frequencies. Again, you need to look at the field and the physics aspect of things. Get good at complex numbers. That's really where it all comes from. I wouldn't say you can't, but I would say it's very difficult to understand these concepts if you don't understand complex numbers. And finally, when it comes to delay, there are different types of delays, and you have to be really careful when you read something or when you write something. What type of delay am I looking at? So define it in the text, what it is. I think that is probably it. So 4 hours, 13 minutes. Thanks for now.